Hello, students.
Good afternoon, sir.
Good afternoon, sir.
Good afternoon. Okay. So still some students are joining. Okay. If you have any question, take in the meantime. Anyone who is improving, not in the first year. Anyone present here?
Yes, sir.
Yeah. Tell me your name.
Harsh.
Harsh. Okay. Yeah, I mean, well, you can't do anything. Some students are still sending the assignment, which is not proper, I think. It's already so many days past, so. And they are not attending the class, so I don't know what they are going to do, because when from the next turn, I told you in the next turn you have to not attend the Tuesday class, and we will have the practical session of 2 hours and then followed by the lecture. So the first on Wednesday will be the S7. Harsh, you are supposed to come on Wednesday, okay?
Okay, sir.
And try to, because I will be taking, like in, for some time I can ask you to learn, and then I might take a quiz. So, and those marks will count, because I have no other way to give you sessional marks. So the best way is to, like I give you that within these 2 hours or 1 hour, prepare a program and upload it. So everyone is supposed to be present here, because I can't tell them separately. So there are other students, they have all joined and they are not aware that they are sending the their assignment by email. But now onward, there will be no email attachment accepted. Okay, so everyone has downloaded and ready with the screen, or anyone has problem?
So I have to ask one thing.
Yeah, tell me.
So when I compile the program and then run the exe file, it usually shows Fortran errors.
A.out. When you compile, you get the A.out is formed.
Sorry, sir.
The exe file is named as A.out. A.out.
Yes, sir.
A.out. If your program is compiled properly, you will end up, you have to do ls and see that the A.out is formed or not. If A.out is formed, then that means your compilation is correct. And then you write /A.out and enter. Then the program will run. Okay, now tell me what you are saying.
No, sir, I thought that we have to run the exe file from the folder, not from the terminal.
Yeah, that is the exe file. A.out is formed. You see, that's why I told you that when you compile, then if your program is okay, then you see ls, you do it, then you will see that A.out is present. If that is, then ./A.out, enter. Then that is the exe file. Did you do that?
Yes, sir. From that it is working, but I thought that we have to run it from the folder, not from the terminal.
No, from the, you have to, the notebook is for making a program, okay? And then when you go in the terminal, then on the $sign, then you write ls. That is what I told you. And you have already notes, my notes there. So if you do ls means list. So you see, you will find your program. Suppose you have named any program file, for example, simp.f or F95, then a.out is formed. You can see that a.out file should not be edited because it's sometimes your computer will hang, and this is in binary, so you don't understand what it is. Okay, so then you find that.
I'd also like to ask a question, sir.
Hmm.
So the script which we are saving after the code which we type, and when we save it, so which format do we use? Because my Fortran is accepting F90, F95, all three of them. So which version will be working on?
The PDF file I gave you, what is written
That
there?
is F95.
F95.
Yes, sir.
Okay, so you can move it to F95. Suppose your file you have named simp.f. If it is F95, then what you do, you can just say move and the file name, that is your simp.f, to another file, simp.95. Okay, and
Okay,
then compile
currently
it.
we will be working on F95, right?
Yeah, this is F95. Yeah.
Okay. Okay.
Anyone else? Okay. Okay, so what I have planned today, that I will tell you some more statement, because it depends on the computer. Some computers accept those statements, some some are not accepting. So you can try, because those are handy sort of statements. So let's see. Yeah, that's but most of them now F95 will take care, I am sure. So let's see. Yeah. Okay, so can you see this slide?
Yes, sir.
Okay, thank you. Okay, now, so I this slide I had earlier also. So input and output, you can utilize all these formats listed here, and these are compatible in all the computer. So A format, as I said, if you write A15, 15 columns are reserved. Whatever you write there in the data file, it will be as such printed there and read that. So D is double precision, and E format is exponential, real negative number, and then integer, logical, X for gap on the line, and slash vertical gap, T tab space. So all these you will remember. I think you can. Then I told you that these are the different keywords of the Fortran 77, and these are also accepted in other Fortran operating system. Okay, then I told you the different arithmetic, logical, assignment, statement, unconditional go-to. So we will go one by one in these and tell you. So what essentially I will be covering here, that arithmetic and logical assignments, unconditional go-to, which I have not told you so far, assigned go-to, computed go-to, these are more variety, and then block, else if, continue is a new, pause I told you, do, undo, I mean how we can do read, write, I told you, and call and return also. Every subroutine should end up with the function with the return, backspace, and close file, all these things. Okay, so let's see input output. This was you have to open this file. I gave you, because one of the example I gave you in my Simpson program, so follow exactly the same, or these are the brief ones, which is you can read here, and don't give format here, give a statement here like this way. So you can read and write in this way, and be very particular about the format that you are giving, FND format, and so on. Now you should know that these are non-executable functions. Like if you write program or function, subroutine, these are only written for the purpose of notation. These are not, there is no execution. So like data, giving data, there is nothing executed in this statement. Similarly, like dimension, common I will tell you today, equivalence I will tell you today, and parameter and external I will tell you today, and then integer declaration. These are double precision, you can declare complex, and data and format. These are not executable statements, means there is no execution involved. But you have to write properly these so that computer accepts it. Okay. Now let's go to the one by one, the control statement. Now the control statement, that means how you control the program, go here or there, test it, do this thing, and do loop it. So these are the logical expression, branching statement, where to go, where not to go. Also jumping after doing this, go to, assign, go to, computed, go to, looping. There are a variety of looping, do loop. Then we had also considered the subscripted variable, two-dimension array system, and then functions of program, and then all these things. Okay, so logical is clearly that, and not, I have told you how to use this variable, logical ones, and this I also logical variable and expression. Like when you write x and y, that means both should be true. X or y, one of them should be true, and these are both not true. So these are the types of logic. Okay, coming to this thing, logical if. The logical if that I told you is one of them, is like if you write if and then some expression here, then if this, so you have to use bracket. So if you write if here, okay, so if you write in bracket something, testing, whether greater than, less than, or whatever, you can write a complete expression here, and not only greater than, you can execute also something like 5 plus 9 into t variable in the bracket, then dot. So, but be clear that you, when you do this, you, in addition to other brackets you can have, and here the parenthesis should always be balanced. It's not 3 parentheses here, 2 here. So it will see that in this case, parenthesis is not balanced. So you have to go from inside to outside. So if this is correct, then it does this, executes here. Here you can give any statement, that executable statement you can give here. You can add or whatever, go to this. So all sorts of things can be done inside and outside. The only thing is when true, it execute this and then comes down. If it is false, then it comes down. Computer always runs from top to bottom. So, and it needs to know everything before it goes to any state. Like when you say any statement, be clear that everything is defined in the beginning. Most of the computer, if you have not defined, may take, like you are using ADX, but you did not define. So normally it should take 0.0, but many computer take anything available in their memory. So it's very dangerous. So always see that when you are coming top to bottom, that all the variables are defined properly. If the logical expression is true, then it executes, and then remember, then it comes down. So you have to be very careful that if it is true, then what you want to do or you don't want to do. So because it will come here, and if it is not true, even then it will come here. So you have to see that if you want to make any condition, when it is true, then it should not come here or what not. So that is very important. Many students, they forget about that. After this, it will come here. They think that, well, this is true, then it's not going to take anything below. No, the only difference is this executes and then comes down. Otherwise, it comes down automatically. It doesn't execute this. So if the, okay, now example like program odd integer. So program odd is a variable, program odd is a program, integer x, y, and rem. You see, all are real in Fortran, but since it's declared, they will be treated like IJK11. Only these particular variable, not starting with x. So then you can print these numbers, whatever you want to print. So since there is no variable to be print, you have simply written these in quotes, so it will print this. So if you don't have anything, just it shows that you want to print the written thing in the quotes. So then read, first it reads x, and then it defines y, x by 2, and now this type of, there are two statements written in a single line separated by semicolon. Now I am not sure that when you are doing this, then it might take or give error. If it gives error, then write y is equal to x by 2, and the next line you write rem is equal to x minus 2 star y. Remember this thing. Not only, maybe today you are doing using some computer, it can take, and some operating system may not take it. So safer is don't use this kind of thing until you are sure, or try it. If it gives error, then you can bring it here down. No, there is no need to discuss about it. That sir, you told me this, how to do it. Now it's not taking. Well, I am telling you that these two statements can be written on one single, but sometimes it is not possible, depending on the operating. So you can see that if it is correct, write this x is odd. So you see, checking, it is a program which checks whether it is even or odd, and writes. If it is not correct, if it is not odd, then so it says that rem. Now rem is here integer, so you can compare integer quantity. No two real quantities can be compared. Like you cannot compare x if it was not integer. So if you compare, as I told you, two real quantities are never equal. So if you want to see that if two real quantities are equal, then better, like suppose we have p and q real quantities. Now P is equal to Q, you cannot test because it will never be equal. So real quantity, you can say P minus Q is less than less than 10 to the power minus 19 something. That means if it is less than this, then that should be equal. That is what it means. So be careful about this. If you don't do this, then maybe I don't know what it is going to do. That's the problem with computer. Sometimes it will not point out error and do it on its own, which can be dangerous. You see, dangerous in the sense that sometimes your whole period is gone 2 hours and you are bothered why I'm not getting answer. So that's very annoying. Remember that. Okay. So arithmetic, if can be used like if this is this quantity or whatever is to be done here, plus, minus, whatever. But if the total quantity comes to be negative, then it goes on a, yeah, you have to give here a statement number like 10, 11, 12. If this whole quantity is 0, as I told you, it will never be 0 completely. So if these are integer, then only you can check. So 0, so you can give 100, 101, 102, or whatever you want, where you want to take it. So this will be negative, this is 0, this is positive. Means test this quantity in the bracket. If you find it's negative, so it should go on the statement number here. If you want to equal or 0 or positive 0 or equal, you can give the same statement number here. So let's see this. Like I have defined DISC B square, in that B square AX square plus BX plus C. Now B square 4AC, for example. So you are testing DISC. If it is, you don't want to take it a square root if it is negative. That means if you find this, so you can send it when. So M1 is the statement number. You see, these are the statement number here. So it goes 100, it goes 101, and now what is the difference? The only problem is that suppose it's a positive, so it comes here, no problem. But if once you say that check it, and if it is 0, then it comes here and then comes here. So you have to put something that after one test is done, then where it should go. So like I can give you everywhere if it is done, whatever you want to do, and then go to, I can give a statement number 15. So continue 15, continue. So it will. So after every checking, send that, because if this is true, directly it comes here. If it's positive, directly comes here. So no problem, here onward it will proceed. But when it is true, it will come here and then comes and then. So you have to have something in between where you want to send. Okay, so block if, else if, or ladder statement. Like this, form 2. If logical expression is correct, then do the execute the statement written here. If it is not correct, then otherwise you do this statement. That's what you are saying. So the same if command that we have used earlier can also be like we had. So the main point is then, and you could also say if you don't want to test. So the advantage over here is like if you use this, then it will not be going to the, it will skip the thing here. So like in this case, it will come here down after 1, then comes here. But if you say and if, then its only problem is that. So this is the basic statement. If checking here, then do this. And if statement finished. But if you know that if you can have other choice, then you can finish the if here and test 2. Now here another one is like you want have 3 choice like in the previous one. So test it, then do executable 1, then do or if it is true, do this thing or the advantage of this statement if is, hold on, there is someone. Let me. क्या किया था? वो जो आप क्लास बना रहे हैं, क्या लिखना? खाली साइन करना है? कोई बात। Okay, sorry, there was one person from construction division of IT. Okay, so you see here the problem is only one of them will be executed and then it finally comes after the end if. While in this case you have to have some more statement, like if this is true then this will come here, while you don't want these to come here. So you have to feed some statement. So that is how you should be clear about it. Okay, so like here you could test if it is less than 0, then negative, it is equal to 0, then here, and if it is greater than 0, then here. So that's what you could do for the same problem. Okay. Yeah, that is what is here. The same problem can be done testing. If it is greater than 0, then roots are real. If it is less than, then the roots are complex conjugate and solutions are real and identical. So if it is minus, then this, if it is greater. So that is what I said, that you have to nest the same thing. So you can see that if you are not having clear cut, this requires 8-9 statements, while this one requires only one thing, that you can send wherever you want. And because you could choose this statement, it jumps there somewhere. So that's not, they are not written in serial order. So M1 goes straight somewhere and finish the program. M2 goes somewhere and finish the program. So that is what it means. So this is a smart if statement, but it depends that how you want to do this. This is a lazy experiment statement. If this, do then, if this, do then, something like that. Okay. So here, that is how you see we have compared to this. This is the one, the equivalent of this is here. Less than this, then go to M1, the same thing. If this is less than, if it is equal to 0, go to else, go to M3, and then. So you can see that this is what is the difference. So you can choose whatever you like. So both are equally available in the, okay. Select case, select I also, but I don't think people use select. Only few people or very standard program use select. So like here, select case, here selector is given. So like if you say case list 1, so a statement it will print. Then if list 2 cases, then this is statement, and then case default statement and select. Okay, so this is the program that you can make a case select cases. Okay, let's not. Okay, looping do loop. So, you know, although I have told you, but here I am emphasizing in a systematic manner. Now there is a do statement and continue. I did not tell you. So That is why you see in my program I have used do label, means statement number. Do up to this statement number what you want to do. Change I is equal to initial value in the final value and in the step value. And then whatever you want to do, this will go here until it reaches the final value and this. Now this continue simply says, if you write continue and couple it with the do loop, that means take the next value. But you can use anywhere, go to something, then continue can be used. Continue simply says go ahead. That's it. So it's very safe. If you do not have any statement, you can write, bring it here and continue, it will go further on. But when it is coupled with the do loop, means go to the next value, next value, next value until final is reached here. Now it says, so this is the main do loop that so what happens that you should not use any subscripted variable here. Like you can't say if x is a dimension, do x something, or if it is now these values should be integer mostly. That is what, then it works properly. Okay, so step size is on, if it is, this one is not written with the comma, then it take automatically one difference. So you don't have to write go from 1 to 50 by each one. But if you have some step size like 1, then 3, 5 or 9, then you can do it. So these are the statements here. So this is now another do loop, do while loop. The do while loop allows a block of statements to be executed repeatedly until the specific while condition is met. You could write just here while logical expression, if it is true, then do this thing and finish the end. So it will go until this becomes negated. That means this is not true. When this is not true, then it will not go to the do statement. As I told you, if it is true, then only it goes. So while this expression is true, do looping do other, and then stop it. So like I could give here do until 100 from 1 to 5. So I can check here that if anything I have written and increasing the value of I, so when it becomes 100, when you can write that I equal to 100, less than 100 do is, so it will do. Otherwise, then as it becomes greater, it will go ahead. Same thing you could write do while, do this thing till that is met, that condition is met, and then and do and go. So do while loop is not a ANSI Fortran 77. Now this statement, when Fortran, if you are having a compiler Fortran 77, then this is not available there. This has come in Fortran 95 or 90, this statement. So suppose you have got a program, old program somewhere, this is 77, don't use this do statement, only use this do statement which it understands. While nowadays these do statement, so correct way is to use if and go to statement. That's what I. Okay, now there are just the example of this. While logical do statement here, whatever statement you want to have here, and then as I said, this is go to statement. You write go to some point, go to some, so that can also be done. So like do looping can also be done. It means by using if statement. So label F, and then so you have to give a statement number here. So it says if this is true, then go to this statement. If this is done, when this is not true, then outside. So you can use if also for do looping. That's a smart way to do. When do loop was not known, people use this type of expression. You see, here you have to get a statement number. It says that check this. If it is correct here, then you send it here, and when it is incorrect, then it simply goes out of it. So here is this I is 0, 100 statement. If x is greater than 0.0, then x is equal to x minus the square root x, I is equal to I. Go to 100. So it goes, after doing this, it goes to 100 again until you see I is increased here, and so also the x is increased. So if x is now this is one thing that I found is students are puzzled, like you are using do 100 I is equal to 1 to 100 by step up to size. It is quite likely that this variable I is not used at all. Only you need I is, so don't be nervous or don't think that it is not right. It is not necessary that this variable I should be used. Another thing I told, you cannot play with this I, you cannot modify, because you have already ordered change this from this to this until this is done. So you cannot modify, like you cannot write I is equal to after some time 4 star I. No, this is not allowed. You can use I, but you can, and even if you have not used I, it doesn't matter. It says that do the variable, so you do this way, and whether you use or not, it's not the business of computer. Simply it goes from one statement to 10 statement repeating. So it's a repetition, that's all. Computer has no need that you should use that variable. There is another do until loop. These things have developed because they become already like you are talking in English. So do until loop keeps the termination criterion at the end instead of at the beginning. Never put the until statement in the beginning. Like in this case, we have put the logical statement in the beginning, like here, while do this thing already. Now, when you are using until, then you cannot start with this. So like do, just don't do, no statement, and until something is true. So it goes here, and suppose you are playing with x is equal to x plus 2. So you can put a check on x here. So if this is true, until this means the same thing. Like you are doing this, then if it is true, this expression, till then it should go here and here, here and here. And then when it is not met, then it goes out. So until can also be used. So depending on that, now all these things you have to remember. So what we have, do end loop replaces do continue. That's what I said, that this was the earlier one, that better use statement do 100 until 100 this point. The same thing is do variable and then end do. So either use continue or use this thing. Both are equivalent. So and now here loop 1 do and do. So there are 3 variety of things that are available to you. Whatever you want, you can choose. There is very interesting one, like cycle statement. Means if instead of loop, you can write cycle. Cycle means just go making cycle 1 time, 2 time, 3 time, 4 time. So when cycle statement is encountered inside a do loop, then one single do loop is prematurely terminated and execution continues with the next loop. So like I have said, do I 1 to 100. Okay, so this do loop finishes here. Inside the do loop, I am checking something. If expression, check this. If it is true, then do this thing. So अगर I mean अगर आप ये देखते हैं कि ये नहीं हो रहा है, or suppose you find this is you want to do loop it, so either put do loop or you just write cycle automatically cycles it here until it becomes untrue. So this is also a smart case that you can use. So it only single statement is correct. Okay. Now there is implied do loop. As I told you in the beginning, implied do loop, you don't write do loop. Implied means automatically understood that it's a do loop. So like you say here that in the bracket I star AI comma BI comma I is equal to 1 3. Matlab, you can use this one when you are having I is equal to 1 comma 3. It simply means that change in this bracket I from 1 to 3. So you see, what does it mean? It will first take I is equal to 1. So it will give you A1 because I is 1, B2. And then when I becomes 2, so it gets multiplied here. So 2A2, B3. And B3 because I plus 1. So you see, you could read this way or not read, but you want to do it. So just do it. It's a same way you can have here I is equal to 4 to 6 and J is written here. So J first this bracket is done. You know, if something is bracket, that will be the inner bracket done first, then outer brackets are done serially. So first you can see here, if you take an I 4. So 4 is written, I is 4, and then this is changed. B1, 2, 3. So you see 4, B1, 2, 3. Then second one is taken. So you should not confuse that you have said this, then the first one starts here. Similarly, AI, BI, J1 to 2, I3. So you can see that this is the way it goes. The inner and outer loops are not interchangeable. You can't change it. It's defined in this way. So this is the simplest way of doing the do loop. I mean, you see, the same thing I achieved here without doing the do loop. I wanted to multiply this by 4 and then gradually like 5 or 6. So I achieved the same thing without using the do loop. That is why it is called implied do loop. You are not saying anything, but it is automatically understood that is a do loop. Okay, implied do loop is how you read these values. So you see, automatically it reads the x1 to x5. Write these things so matrix can be written inner, outer. So these are the different examples you can use for implied do loop. So loop inside do loop is the same thing like do you have 3 loops. So that I told you that this will be completed, this, then this will be completed, and this. So what you can see that you cannot from inside you can jump anywhere outside. You can use go to statement, can jump side. So this is the do loop of writing also can be done in the same way. So instead of you would have implied do loop, otherwise you have to write this way. So, or if you have changing 3 variable, you can change this. This here also you can do 100, do 200 and this, then 200 continue 300, then 300 continue 200, then 200 continue. So that's also the same thing, do loop you can do. Jumping statement, go to statement. when go to statement is used, you are not using it with if or anything. Then you just write go to 17 or go to 50. Wherever you like, you can make in a program after certain segment you don't want to, you want something to be skipped, you can do that. So a go to statement can be used to transfer control from if and do blocks, but not into them. So if you are using this in a do loop, you can use go to anywhere. If no, you something it does and you say after it has done go to out, but you cannot bring anything inside. Do looping cannot be modified from outside. However, do loop can be broken from inside. You are in the do loop, something you are checking that take a square root, and if quantity becomes negative, then jump out of the do loop rather than doing all of them and getting into trouble. So that is what go to is. And also sometimes for debug of the program, go to is very important. Certain you want to check something, then go to skip something and test it. Now, what is computed go to and assigned go to, that I did not tell you. So this is in the next slide. Arithmetic, if it looks, it's a repeated unconditional. Okay, that slide was not required. So here, unconditional go to. You see here, you are doing the do loop system can be done here. That if so long x is less than this, go to 10 here and do this job. And once it is done, so that means there is coupling this is a statement, but so that is why it says unconditional go to. Go to is not built in the if statement, it's a separate statement. Go to 10, go to a statement where you want, simple. Okay, there is another very smart go to known as computed go to. So here is the example. You write go to 10, 20, 30, 40. These are the statement numbers. Go to this is a. Now see, you don't have to put n is equal to. Sometimes students confuse with this. If it is 1, then go here. If it is 2, then go here. If it is 3, so it only follows the sequence that if n is 1, go on this statement. If it is 2, go on this. So it is what is written here. 10, write something. Your choice is 1. So if it is 1, first it is. Second statement, go to the sequence. Second, yes. Anyone? Some question? Okay. So go. Your choice is if it is 3, then. So you can write the different statement. Like if a statement negative positive can also be achieved here 10, 20, 30, and then you can type this. So you can use this. I very much use this go to, which is very good and with okay. So computed go to versus the block. If you can see that this thing, if you can achieve with 3, 4 statement, like go to here, I am jumping out. If this is, then go to label 1, come out of it, and other and if this is true, then otherwise what will happen? It will check automatically here and then here, and then comes end. So this can be achieved simply by giving label 1 and label 2 here itself. Just write 1 goes label 1, 2. So you have to select the 1, 2 here, then it go to the. So you can see it's clearly because you are making a smarter program. Assigned go to is also very interesting go to. In this case, what you do, you assign some value to an integer here. In this, like n is equal to 5, and if n is equal to 5, then go to the here. Now statement number is important. So let's see some examples should be there. Yeah, it's better to understand. Assign 40 to n variable. That means make n is equal to 40. go to 40. So you see, if 40 is there, it will go to 40. If I say assign this to this number, then 20. So it will go to 20. So it's coupled with two statements. Assign some variable and then choose the statement here. While in computed goto it was sequence and follows the sequence. While assign goto it follows the statement number written. You see, like it is 40, then it goes to 40 stop, emergency stop. Stop can also be used very nicely for debugging the program. If you are checking some portion, then you check this and say stop. So it will stop there. Then check some portion more and then stop. So that, okay, so pause and stop that I had not told you can be used. Stop means computer immediately stops the execution and comes out. Pause means you are asking something, just wait there. So that means sometimes you say pause there. So, and you want to feed some data, so it will pause until you give the data, then it proceeds. Common statement. Now this is most beautiful expression. Like in some cases, you want some quantity to be passed on to the subprogram or the other program. So you use common blank, then X, Y, J, and then put the same common over here. So if you write common A, B, J, then X value is taken as A and Y value is taken as B and I is taken as J. So that means you can transfer the value from here and not necessarily use the same variable. This is known as unlabeled common. But if you have written common name and variable list, so some of the common will be sent. Here you can write common slash number 1 or something, then it is number 1 common. So this type of statement is used, and then you use the list. Those values normally, like you have a constant, Bohr orbit, pi and so on, so which can be, instead of typing here the same thing, you could pass on this from main program to a smaller subprogram. And here, like if your list is like here you have 3 lists. If you give simply A, B, then first 2 values are taken, third value is not taken. So but if it is a labeled common, then whatever value you have given there should be the same storage here. So this is what you have to check. Now this statement is very good to use it. I use it a lot, this, because so the most lazy person or the laziest person is the best programmer, that you don't want to write too much, but you can use. So common statements, it is not necessary to declare named common blocks and use there. These named common blocks must be exactly the same length wherever they appear. Blank common without label cannot follow the same thing that I told you. The number should be equivalence. Now this equivalence statement is not very useful nowadays. Earlier, suppose you have a dimension of any quantity A as 1500. And you want that the for B you again have a dimension 1500 storage. So what happens that A, while it's doing calculation, A 1500 is dimension, B also, so this becomes 1300 dimension. So similarly, there are so many dimensions. So you can say that, well, while doing the calculation, use A dimension equivalent to B dimension. So after finishing the calculation, A, B dimension. So it's not that you have to declare A, B 1500, 1500. You say equivalence of A and B. So list here which dimension should be, which equivalence you are giving to the variable. Which variable are like A, B are equivalent, then it will take A 1500, B 1500, so both will be shared by itself. But remember that after doing calculation, if you want to use the same variable storage, you can do. External statement like you are using a sub-program in a sub-program. So it doesn't know that is, so you can say externally it will require some program. Yeah, in the common, I told you, common should not mostly unlabeled common are in the have to be commons should be there in the main program, but labeled common not there. Like one set of quantities transferred from one subprogram to another subprogram can be done. Okay, so external statement, I told you, you have to declare, it's a declaration that what you are going to, then comes the compiling and program and so on. So that's all for today. If you have any question, students.
No, sir.
Okay, so now all the statements required for a perfect programming are known to you, and you can use these in your program. Now it depends how smart you are in using them, because you can make the program accordingly. Okay. So let's see, we will run some, I will tell you some program that you can make and run there in the next. And then both the group should join at 2 p.m. for the my lecture. That will now be for the numerical analysis. That certain program integration, differentiation, or different type of extrapolation that we will learn, so that you know that how to solve this problem, how integration can be done numerically without doing analytically, and then how to make a program. So program is a language that translates your mathematical steps to the computer, and how computer stores that I told you earlier. So that makes a complete familiarity with the computer and the language computer understands. Okay, that's all for today. Okay, any question?
Sir, so the common state is to transfer variables from one function to the other function in the same program.
Function is not transferred, variables are transferred.
Yes, sir, the variables.
Yeah, variables you can transfer this, and yeah, that's it. Like suppose you have a
Yes, sir.
Yes, sir.
Thank you
Yes.
for confirmation. Right. So we saw the definition of the limit, and we have also seen one example for calculating the limit using the epsilon delta definition. And now we will see some more examples. So let us consider
Sorry. So you are not for your phone.
Sir, your network is lagging. Sir, nothing is clear, sir, in your voice, sir. I think you have a network issue, sir.
Okay. Am I audible? Can you hear me?
Yes.
Yes, sir.
Yes, sir, we can hear you. You are audible.
Okay, so now is it fine?
Yes, sir, it is fine.
Okay, so I was saying that we go along the path y is equal to mx. So what we do is we substitute y is equal to mx in this expression, that is the value of the function. So when y is equal to mx, the numerator will be mx square, and the denominator will be 1 plus m square x square. And then you take the limit x goes to 0. So clearly x square and x square cancels out, and you get the limit as m divided by 1 plus m square. So this depends, the limit depends on the value of m of this line. In which case the value of m will be 1 and the limit will be 1 over 1 by 2. If I go along the path y is equal to 2x, which means m is equal to 2, and the limit will be 2 over 5. So along these two paths, I get, so this shows that the limit does not exist. So this depends on the value of m and is different for different value of m. This means that the limit is path dependent and hence the limit does not exist. Okay. Alternatively, I also said that you can calculate the limit by converting the rectangular coordinate to the polar coordinate. So if I do this for this example, which means if I take x is equal to r cos theta, and there is a typo, y is equal to r sin theta, then this function will become r square sin theta cos theta divided by r square. Okay, and the limit xy goes to 0, 0 will become r goes to 0, because r is the radius of the circle. So you take the radius towards 0. That means you are coming from all directions inside the circle when r goes to 0. So when r goes to 0, you get the limit as sin theta cos theta. Now this limit depends on the value of theta, right? So that means if you are approaching the point, let us say this is the point 0, 0, and you are approaching the point from these directions. So this is essentially says that the limit will depend on the angle on which you are approaching the point 0, 0. Okay, so if you change the angle, the limit will be different. So this means that the limit does not exist, because if you take the different radial paths, for different radial paths, the value of theta will be different, and therefore the limit will be different. Okay, so for the same example, you can show either using the Cartesian coordinate by taking let's say for this straight line in this example, or converting the Cartesian coordinate to the polar coordinate, and then calculate the limit. So in both the cases, we see that the limit is path dependent. Therefore, the limit does not exist. Fine.
Excuse me, sir.
Yes.
Sir, हर बार मतलब अच्छा.
Sir, can you please explain the first part? Your voice was disturbing then.
What is the question? Can you repeat it again?
Sir, can you please explain the first part of the A?
Okay, first part of the A says that I take a path y is equal to mx. Right? So you put this value here. Part of the A says that I take a path y is equal to mx. The denominator you have y. Right? So you put this value here. Part of the A says that x square common. This x square cancels out. The limit xy goes to 0, 0 is basically, this is another typo here. R goes to 0. And this limit is 1m over 1 plus m square. So this means that the limit is, limit depends on the value of m. And what is m? M is the slope of the line. Right? Slope of the line y is equal to mx. So limit depends on the slope of the line. If you take, if you come along the path y is equal to x, the value of m will be 1, and the limit will be 1 over 2. If you go along the path y is equal to 2x, the value of m will be 2, and the limit will be 2 over 5. So along path y is equal to x, the limit is 1 by 2. Along path y is equal to 2x, the limit is 2 by 5. And they are different. So along paths, we get two different limits. Right? So the limit does not exist. Is this clear?
Okay, sir.
Is this clear? Yeah. So now let us consider the second. Yeah.
Sir, I have a doubt, sir. So, sir, whenever we have to calculate a limit, we have to let y equal to mx or in Cartesian form.
No. If you want to show that the limit does not exist, then you consider two paths. In that case, you will try whether. So sometimes it happens that if you take y is equal to mx, along all the paths y is equal to mx, you will get a limit. Okay. So it may happen that this quantity may become 1 in some example. So along this path, you are getting the same value, even if the value of m is different. Right. In that case, you can try with y is equal to mx square. Sometimes this also may fail. So you can try with y is equal to mx cube. Right. So you keep trying until you get something which is path dependent. And then you can say that the limit does not exist.
Sir, may I ask one question more?
Yeah.
Sir, in the last class you calculated a limit from the last example, sir. Sir, I was unable to understand it, sir, because I tried understanding it after the class, sir.
I cannot go back to the same lecture again and again. If you have some specific question, you can ask me after the lecture.
Oh, okay, sir.
Okay, but the message is that if you want to show that there is a limit, you have to use the epsilon delta definition. If you want to show that there is no limit, then you identify two paths along which you get two different limits. And then you can say that the limit does not exist. All right. But if you are not able to understand, or if there are a couple of more students who are not getting it, then I can have some extra time. I can fix some extra time after the lecture. Okay.
Thank you, sir.
Now consider the second case. Y is in this case y is equal to, you take y is equal to mx square, and then you see that the limit comes out to be plus minus infinity. Okay. So in this case also the limit does not exist, because along the path y is equal to mx square, the value of the limit is either plus or plus infinity or minus infinity. Even if it is plus infinity in all the paths, the limit does not exist. Okay. Now consider the third case. In the third case, we can take y is equal to 1. So you take y is equal to 1. So this will become tan inverse 1 by x, and then take the limit x goes to 0. You have tan inverse plus minus infinity. Okay, and tan inverse plus minus infinity will give you plus minus pi by 2. Okay, so here you do not get a unique value of the limit, so therefore you can say that the limit does not exist. The limit is either plus pi by 2 or minus pi by 2 when x approaches to 0 along the path y is equal to 1. Okay, so here also we can say that the limit does not exist.
Sir.
Okay. Yeah.
सर yesterday you said कि सर जो लिमिट टेंडिंग में जो वैल्यू दिखा रहे हैं सर वो पुट करके हम चेक नहीं कर सकते सर.
सॉरी
सर आपने कल बोला था कि सर हम ये जो वैल्यू टेंड कर रहे हैं वो पुट नहीं कर सकते उसमें. वो रॉन्ग है सर.
डिटरमिनेंट फॉर्म बन रहा था उस समय.
किसमें पुट नहीं कर सकते
सर? हमने जो कल लास्ट में एग्जांपल किया था सर उसमें सर आपने बोला था 0 0 करके 0 by 0 फॉर्म देखते हैं बच्चे उसमें.
नहीं तो यहाँ पे तो इन्फिनिटी हो गया ना. 0 by 0 फॉर्म कहाँ है यहाँ? 0 by 0 फॉर्म नहीं है ना यहाँ पे. ठीक है,
मतलब सर पुट कर सकते हैं.
क्या मतलब पुट कर सकते हो? वैल्यूज तुम बोल रहे हो पुट कर सकते हैं. वैल्यूज नहीं पुट कर सकते. वैल्यूज
चेक करने के लिए
कर सकते. ये यहाँ पे इस पाथ के अलोंग आइडेंटिफाई कर रहा है. y इज इक्वल टू 1 का पाथ ले लो. ये है ना कार्टेशियन कोऑर्डिनेट में, तो y का वैल्यू 1 ले लो. इस पाथ के अलोंग x वेरी कर रहा है. अब इस पाथ के अलोंग अगर तुम 0.01 पे जाओगे इस पाथ के अलोंग, तो तुम्हें दो लिमिट मिल गया. एक प्लस मिल गया, एक माइनस मिल गया. प्लस पाई बाय 2 मिल गया, एक माइनस पाई बाय 2 मिल गया. ठीक है.
यस सर, डाउट क्लियर्ड.
राइट हैंड साइड से आओगे तो पाई बाय 2 पे आओगे. लेफ्ट हैंड साइड से आओगे तो माइनस पाई बाय 2 पे आओगे. तो along this path you get two values. So the limit does not exist. I am not putting the value here. I am just identifying the limits along the path y is equal to 1. Right?
Yes sir, yes sir.
Now we have an important remark. It says that when you apply the transformation from the rectangular coordinate to the polar coordinate, this must be used with care. Right? You cannot immediately apply and then conclude that there is a limit. It must be used with caution. And this caution word is important here when you make this conversation. And why this is important, we will illustrate this with an example. So let us consider this example. Now you change this to the partition to the polar coordinate. So polar coordinate, the changed value will be this one, and r square will cancel 2r here. So you get r cos raised to 3 theta, and then you take r goes to 0, the limit is 0. Okay, so it seems that the limit does not depend on theta. Okay, but then you have to apply the epsilon delta definition in the polar coordinate to really conclude that this is a limit. Okay, so first you make the conversion, then calculate the limit in the usual way as if you are dealing with a function of one variable where the only variable is r, and then you get some number. In this example, you get the limit as 0, and then you can verify that this is indeed a limit or not using the epsilon delta. So that we will verify. So we say that the limit is 0, so this is the function, and this is the limit. This function is converted to the Cartesian coordinate, polar coordinate. So this function is equal to r cos square cos raised to 3 theta. Okay, and cos is between 0 and 1, so I can say that this is less than equal to r. Okay, so mod of cos raised to 3 theta is less than equal to 1, so I can say that this quantity is less than equal to r, right? And then you take r less than epsilon and choose a delta less than epsilon. So r will be less than delta, and since r is less than delta, so r and delta 0 and epsilon, so r will be less than epsilon also. Okay, so here we get less than epsilon, the value of the function. In fact, the value of the function in the polar coordinate is less than epsilon for r less than delta, where delta is at the limit of in this case is 0, right? So keep in mind that if you only show this step, if you only show this step, and you can conclude that the limit is, and you conclude that limit is 0, then this will be partially true. I will say this is not in fact true, because you only say that the limit along certain path is true. So this step is used to guess the limit, and once you guess the limit, you can use the epsilon delta definition in the polar coordinate to conclude that this is indeed a limit or not. Okay, so that is why I say that when you convert this to the polar coordinate, you should be cautious to make any conclusion about the limit. Fine. So now let us consider another example, and this example will in fact convince you that this cosine is really needed. Now let us consider this example. So again, convert this function to the polar coordinate. So polar coordinate, you get this, and then you take r goes to 0, you get 0. So from here, can you conclude, if you conclude that the limit is, can you conclude that the limit is 0? And the answer is no. Here we cannot conclude that the limit is 0. Even if the value of the limit is independent of theta, then also we cannot say that limit is 0. And the reason is that if I go along the path y is equal to mx square, the limit will come out to be 2m over 1 plus m square. And this is path dependent. Okay, so this step you only conclude, from this step you can only guess that the 0 might be a limit. You cannot conclude that 0 is limit. 0 might be a limit, and then you can verify whether 0 is indeed the limit or not by using the epsilon delta definition. Okay, otherwise your conclusion will be wrong. Is this fine? Okay, so this conversion should be used with caution. Now there are certain home assignments that you can try. Some problems are listed here, so you can try with all these epsilon delta definition, all these questions at home. Okay. So yes. Any question so far from this limit section? If no question, I can move to the continuity part.
Sir, one doubt.
Yes.
Sir, rectangular to Cartesian, there is this error. Can you explain deeply about this a little? Why is this error?
Which error?
Uh, in the above example that we saw about the
You mean
limit.
when we do the conversion or at intuitive level, why is it so?
Yes. Why
If
there's
you
a
look at this expression, without taking the limit, this expression indeed depends on the value of
ah,
theta.
yes.
And this angle of theta does not appear when you take the limit. Okay. Similarly, here also, this conversion depends on the value of theta. Okay, so that is why we should be careful about making any conclusion, because it may happen that when you take the limit, the angle theta may be affecting the limit. So that you have to verify with an extra step using this epsilon delta definition.
Yes, sir.
Is this clear?
Yes, sir. Yes, sir.
Okay. Now let us go to the next definition in this section, which is continuity. And the definition of continuity is similar to what you have learned in your high school. It is same. You calculate the limit. You say that the value of the function is defined at the point, and the limit and the value of the function coincide. Okay, so this is what all the conditions are written here. Function is defined at the point x naught y naught. The limit exists, and the limit is equal to the value of the function. Exactly the same definition. Okay, so that means in order to show that the function is continuous, you have to verify these three conditions. First, you will verify whether the function is defined at the point x naught or x naught y naught or not. If the function is not defined at the point x naught y naught, then you can say that the function is not continuous. And when I say the function is not defined at point x naught y naught, this means that the value of the function will approach to plus infinity or minus infinity. Okay, something like that. If the value of the function is defined, and maybe in indeterminate form also. Now, if the first condition holds, then you check the second condition. That means if the function is defined at the point x naught y naught, then you go to the second step to check whether the limit at point x naught y naught exists or not. If it does not exist, then you say that the function is not continuous. If it exists, then you check the third condition, that the value of the limit is equal to the value of the function. Okay, so if these three conditions are satisfied, then we say that the function is continuous at the point x naught y naught. In terms of the epsilon delta definition, you make certain changes. So now we say that we know this the definition. This what does this notation says? This notation says that for every epsilon, there exists a delta greater than 0, such that if you take the point from the deleted neighborhood y minus y naught whole square under root, then this will imply that the value of the function is close to the point L. Okay. Now, in the definition of the limit, I said that even if the function is not defined at the point x naught y naught, then also the limit can be calculated. Now, the function is for the continuity, we must have the function. The function must be defined at the point x naught y naught. That is the first condition. So that means the function is defined at point x naught y naught. right? So that means condition that imposed on the deleted neighborhood, deleted delta neighborhood, that condition we can remove. So we had this 0 strictly greater than 0, so that we can say that so if in the case of limit, we were working on the deleted delta neighborhood around the point x0 y0. Now this deleted delta neighborhood is not required for continuity. Deleted delta neighborhood will be replaced by the delta neighborhood of the point x0 y0, where the point x0 y0 is also a part of the neighborhood, is also the part of the neighborhood around the point x0 y0. So this is removed. So now we have this when you remove this means that x0 y0 is part of the neighborhood, delta neighborhood. Okay, and the last condition says that the limit is equal to f, the value of the function at point x0 y0. So that means the limit in the this L will be replaced by the value of the function at point x0 y0. Okay, so this will become the definition in terms of epsilon delta, definition of continuity in terms of epsilon delta. So we say that function is said to be continuous at point x0 y0 if for every epsilon there exists a delta such that the difference between fxy and fx0 y0 is less than epsilon whenever the point xy is coming from the delta neighborhood of the point x0 y0. Okay, so this is the epsilon delta definition. So that means whatever you have done, whatever examples you have done in the case of limit using the epsilon delta definition, all those things can be done here. All those tricks that whatever tricks you have learned in the calculation of the limit, all these tricks will be can be used here using this epsilon delta. Okay, and if you are not able to find for this definition says that for every epsilon there exists a delta. So that means to show that the function is not continuous, if there is an epsilon which is positive, such that for which there is no positive delta, then we can say that the function is not continuous. So for every epsilon you have to look for a positive delta. So if there is one epsilon or more than one epsilon for which you cannot find any positive delta satisfying this condition, then you can say that the function is not continuous. Okay, now if the function is not continuous, then there are two types of discontinuity. If the function is not continuous, then we can say that the function is discontinuous, and there are two types of discontinuity. First is the removable discontinuity. Removable discontinuity means you do have a limit when x and y approaches to x0 y0, then you have a limit which is L, but the value of L is not equal to the value of the function at point x0 y0. Okay, so this type of discontinuity can be removed. And how you can remove this type of discontinuity? You can redefine the value of the function at point x0 y0 as L. So if you say, let us say that the value of the function at point x0 y0 is something else, like which is different from L. So in order to remove the discontinuity, what you can do is you can redefine the value of the function at point x0 y0 as L. Okay, so that is removable discontinuity. Other type of discontinuity is is not removable. So all other types of discontinuity are not. All other types of discontinuity are said to be non-removable discontinuity. For example, if the limit does not exist, then it is you cannot remove this type of discontinuity. Okay, fine. Now we say that a function is continuous inside a domain D if the function is continuous at every point in the domain. So here in this definition, we talked about the continuity of the function at a single point x0, y0. Now, if the function is continuous at every point of the domain of the function, then we say that the function is continuous in the domain D. Okay, so this is known as continuous function. Okay, so graphically it is shown here. It is similar to what you have already seen in your high school, this geometrical interpretation of the limit. So you can see that on the y-axis you have, on the z-axis in fact, because you have 3 dimensions x, y, z. So on the z-axis you have the value of the function fxy, and we say that the limit of this function is when xy, y0, xy approaches to x0, y0, the limit is L. And you see that we had this condition in the epsilon delta definition. So from this condition, what do you get? You get fxy is lying between L minus epsilon to L plus epsilon. Okay, so you can identify what is L plus epsilon. On the z-axis, L plus epsilon, and this is L minus epsilon, and this is the point L. Now you take any value of f inside this interval. Okay, so on the surface you will get some portion on the surface. If the value of the function is sitting inside the interval L minus epsilon to L plus epsilon, then you get some portion of the surface here. The projection of this surface on the xy plane is this one, and this should give you a neighborhood, delta neighborhood around the point x0, y0. Right? So if the function has a limit, this will give you a delta neighborhood. If the function is continuous, then also it will give you a delta neighborhood. Okay, so this is the geometrical interpretation of this, and this will hold for every epsilon. Whatever epsilon you take, this will hold. So even if you had this interval L plus epsilon and L minus epsilon here, you can enlarge your interval L plus epsilon and L minus epsilon. You take different epsilon, some other epsilon, so you have this bigger interval, and then you again do this projection. You should get a neighborhood of the point x0, y0, delta neighborhood of the point x0, y0. You can also decrease the length of the interval. You can take some smaller interval here. Okay, so whatever, as long as epsilon is positive, you can construct this interval, and then you identify the projection of the surface. This projection should give you, this projection of the surface in the xy plane, this projection should give you a delta neighborhood around the point x0, y0. If this is the case for every epsilon, then you can say that there is a limit, and you can also say that the function is continuous. Okay, so this is the geometrical interpretation for both the limit as well as for the continuity of the function at point x0, y0. Is this fine? Any question here? Any question?
No, sir.
Okay, so I'm just checking I'm still online or not. Okay. Now let us move further. So here it says a continuous function. If you have a continuous function, then it will attain its maxima as well as its minima at some point in the closed and bounded interval. So if the domain of the function is closed and bounded, then the function will attain its maxima as well as its minima. Okay. And if mu is between the minima and the maxima, then there will be a point x0, y0 in the domain of the function such that the value of the function will be equal to mu at this point x0, y0. Okay, so this is another property of the continuous function. And the last property of the continuous function is if a continuous function takes both positive and negative values in a closed and bounded domain, then it also takes a value 0 at a point in the domain. Just like you have this is just like the property that you had for the function of one variable. If the function is taking negative value as well as the positive value and the function is continuous, it is bound to touch the x-axis at some point where the value of the function will be 0. Okay, so this is also quite obvious. Now you can see that there are a couple of examples given on the slide where you have to show that the following functions are continuous at the point 0, 0. And maybe some examples where later where you have to show that the function is discontinuous. So let us go. I will not discuss all the examples here. I will just pick one or two examples in this, and then other examples you can read on your own. So let us see that we want to check this first function, whether this function is continuous or not. So what we do is, to make our life easier, what we do is we transform this to the polar coordinate by substituting x is equal to r cos theta and y is equal to r sin theta. Okay. For continuity, we will consider this difference. For limit, we consider this difference fxy minus L. Now for continuity, this L is replaced by the value of the function at point x0, y0, right? And in our case, the point x0, y0 is 0, 0, right? So that is why we are considering the difference fxy minus fx minus fxy minus f0, 0. Okay. So what is the value of the function at 0, 0? That you can see from the definition of the function, the value of the function at 0, 0 is 0. So this value is 0. And this is the value of the function, this one. And when you make this transformation to the polar coordinate, this will result in this expression again. Okay, you can check these transformations easily. Okay, so you get final expression you get is this. Now cos is less than 1. So you can say that this is less than equal to 1. You can also say that sine is also less than equal to 1. So you can say that this is also less than equal to 1. Therefore, combining these two together, you get this whole expression strictly less than or maybe equal to also 5r square. Okay. Now you want to make this less than epsilon, right? You want to make this less than epsilon, and accordingly you have to identify a delta so that r is less than delta. So if you choose this delta, if you choose delta is less than epsilon by 5 square root, and the neighborhood of delta neighborhood of the point will be r less than delta. So if r is less than delta, and delta is less than square root of epsilon by 4, so we can say that r is less than delta, delta is less than epsilon by 5, root under epsilon by 5. So r will be less than root under epsilon by 5. And if r is less than root under epsilon by 5, then r square will be less than epsilon by 5, and this will imply 5 r square is less than epsilon. Okay, right? So that means we are able to identify for every epsilon, we are able to identify a delta. For every epsilon, we are able to identify a delta, which is, okay, let me repeat it again. So for every epsilon, we are able to identify a delta, so that delta is strictly less than square root of epsilon by 5. Then this condition r less than delta implies the value of the function, the difference between fxy minus f00 is less than epsilon. Okay, so therefore we can say that using the epsilon delta definition of continuity, we can say that the function is continuous at point 0, 0. Okay. Now let us consider the second case. In the second case, what we do is we make this transformation. X plus 2y is equal to t, and then take t goes to 0. So if x plus 2y is equal to t and t goes to 0, if you take t goes to 0, this will imply that you are coming towards the point 0, 0 from all possible directions, right? You can easily plot this for different values of t, for positive t as well as negative t. Okay, so you can have x plus 2y is equal to t when t is positive. Plot this, right? And then you can have x plus 2y is equal to t where t is negative. Okay, so you will see that you will have something like this for t positive and negative values. And then when you say that t is approaching towards 0 from the positive side, you are coming towards 0, 0 from this direction, from some direction. So you can check this using this by plotting this graph. And similarly, if you say that when t goes to 0 from the negative direction, then you cover the other direction, other part. Okay, so by making this substitution, basically you are saying that I am approaching to the point x to the point 0, 0 from all possible parts 0. T can approach to 0 from positive direction as well as negative direction. Okay, so this notation means you are approaching towards 0 from both positive and negative direction of 0, 0 from all possible directions. Okay, so you make this substitution in this expression. So this is also a technique. So you should remember that these are whatever methods you see on the slide. These are some of the techniques that can make your life easier. In some example, this technique that I'm will work. In some example, we transform it to the polar coordinate techniques to identify the limit, 4, 5, or you can also say that 4, 5 to show that there is a there is a continuity of the function. So all those techniques you just try to understand and then use this in different examples. Okay. So we substitute this value x plus y is equal to x plus 2y is equal to 2 is equal to t in this expression. So we get this function will become this this one, and the limit x y goes to 0 0 will become t goes to 0 0, t goes to 0. Okay, and then you take calculate the limit in the usual way as if you are dealing with a function of one variable. This will come out to be 1 by 2. Okay, and you can check that the value of the function at 0 0 is also 1 by 2. This is given in the example here. The value of the function at 0 0 is 1 by 2. Therefore, we can say that the function is continuous at point 0 0. Right?
Sir, in rectangular, so in rectangular coordinates, we don't need to further verify using epsilon delta, right? Sir, in this question, we don't need to further verify using epsilon delta definition.
No, because you have already covered all the directions.
Okay, sir.
By this transformation, you have by this transformation and by taking t goes to 0, you have already covered all the directions. I think you should plot this as I suggested in the beginning of this example. Plot this x plus 2y is equal to t in the xy plane, and then see when t goes to 0 from the positive direction, which region you cover, and when t goes to 0 from the negative direction, which region you cover. So you will see that you cover all possible directions, and therefore this is a correct approach to identify limit. Okay. But so it does not mean that you should always look for this transformation in all the examples. In this example, this transformation works, but sometimes it may not work. It may become complicated if you make this such type of transformation in other example. So that you have to use your own brain, your own creativity. Is this fine?
Yes, sir.
Okay, good. So now we have some more examples. So consider this example, first one. So here you can see that if I go along the path, y is equal to m square x square. Even if you just write m, that is also fine. So m squared is written just to. You can also take just y is equal to mx square. M square is written just to make sure that there is no square root of m in the expression, but that is fine. You can also use y is equal to mx square. So when you put this here, what do you get? You get this one. And this x square cancels out. When you take the limit x goes to 0, you get this one. Now this is dependent on m. This depends on the value of m. This means that as you change the value of m, when you change the value of m, what happens? The shape of the parabola will change. You have y is equal to m square x square. This is a parabola. The shape of the parabola will change if you change the value of m. So along different parabola, you approach to different points when you approach to the point 0 0. So therefore, the limit does not exist. Okay. So for the first part, the limit does not exist. Now let us see what happens in the second part. In the second part, the limit exists. In the second part, limit exists. So what we do is we verify using the epsilon delta approach. So this is the function we have, and 3 is the limit point. This is the limit point. So you apply some calculations here, and then you get this one, and from there you get this is equal to mod x minus 2. So if I this is basically the difference fxy minus 3. This is equal to x minus 2. This calculation we have shown here. Now, if I say that this is less than epsilon, and I choose a delta strictly less than epsilon, then we see that we can create this neighborhood. This is the delta neighborhood. Delta neighborhood around the point 2,2. So whenever this holds, this will mean that x minus 2 is less than delta. And delta I have chosen cleverly by saying that delta is less than epsilon. So x minus 2 will be less than epsilon. And if x minus 2 is less than epsilon, that means the difference between the function and the value 3 is less than epsilon. Okay, so whenever this holds, whenever the point xy is coming from this neighborhood, this delta neighborhood of the point 022, then the value of the function is close to the point 3. Okay, so that means the limit exists in this case. Now we see whether this limit is equal to the value of the function or not, to check the continuity. Because from here we can conclude that whenever xy approaches to 2, the value of the function is 3. Now we check whether this 3 is equal to the value of the function or not. So here, this was the second example. So here we see that this is not the case, because the value of the function at point 22 is 4. Value of the function is 4. 4 is not equal to 3. So this means that the function is not continuous at point 22. Right? So if function is not continuous, this is a type of removable discontinuity. This is type of removable discontinuity. And how will you remove this discontinuity? You can see that the value of the function at point 22 is defined to be 4. So if I just delete this 4, and I say that the value of the function is 3 at point 22, then the function will become continuous. Okay, so in this way you can remove the discontinuity. So although we have the discontinuity here in part B, but this type of discontinuity is removable discontinuity. How about the discontinuity in part A? Is it removable discontinuity? Anyone?
No, sir.
Part A also we have discontinuity. Very good. It's not a removable discontinuity because the limit does not exist. So if limit does not exist, then you cannot remove this discontinuity. You can see that the second condition in the continuity is that the limit must exist. So if this condition is not satisfied, you cannot remove the discontinuity. Okay. So we have one example where discontinuity cannot be removed, which is part A, and we have one example where discontinuity can be removed, which is part B. And then we have some homework here, so that you can try. And now before I conclude today's session, I can just quickly go in a couple of minutes, 1 or 2 minutes. I've already said something about this in the last lecture, but let us revisit it again. So this relates to the iterated limit. And this is also given in the tutorial sheet. So if you solve your tutorial sheet, you will see this topic there. So here we have a function fxy, and first I freeze this x. So we freeze this x and then take the limit y goes to y0. So the limit will depend on the value of x, which we denote by gx. Okay, and then I take the limit x goes to x naught for this gx, and let us say this value comes out to be L. Okay, so in other words, first take the limit y goes to y naught, then take the limit x goes to x naught. This iterated limit comes out to be L. Okay, this is repeated limit. Okay, now you change the order. You change the order of the limit. So instead of freezing x first, we freeze the value of y first. So freeze value of y, then take the limit x goes to x naught. This will be a function of y. Call this as gy, and then take the limit y goes to y naught. The value that you get is, let's say, denoted by L dash. So here you have an iterated limit where the limit is taken over x naught first and then over the variable y. So limit is first limit is x goes to x naught. The second limit is y goes to y naught. So only you change the order here in the second case. So you get in one case you get L, in the other case you get L dash. So L and L dash may not be equal. May not be equal in all the examples. And this can be illustrated with some examples here that I have given here. So in this example, you can see that when you take y goes to 0 and then x goes to 0, the value will come out to be 0. And if you change the order, that means when you take x goes to 0 and then y goes to 0, you get 0. So in this example, both the iterated or repeated limits are same. And you will see that this is also equal to the limit of the function. So limit is also same. So in this example, all these three are same. The limit, the iterated limit, both the types are same. In the second example, you can see that this limit does not exist. The limit does not exist, but the repeated limit exists. When you take y goes to 0 and then x goes to 0, you get -1. If you take x goes to 0 and y goes to 0, then you get +1. So repeated limit exists, limit does not exist, but the repeated limit or iterated limits are not equal. Okay. Now in the third example, when you take iterated limit by taking y goes to 0 first and then x goes to 0, you will get 0. But when you change the order, that means you take x goes to 0 and then y goes to 0, then this limit will not exist. Okay, clearly you can see that this does not exist. It will fluctuate between plus and -1. Okay. So one iterated limit exists, but the other iterated limit does not exist. Right. So this is this slide illustrates that limit and it repeated limits are different things. You should not confuse with them. Okay, and then we have some homework that you can try. And I think I will stop here today. Next class we'll start with partial derivatives. Any question?
Sir, one doubt.
Sir, limit.
Go on.
Sir, I was asking that if repeated limit is like we are taking along a path, right, where we put one variable as constant. So, sir, in the first example, your repeated limit was same as the limit. So, sir, if we are saying repeated limit is checking along one particular path of a constant variable, so, sir, how we can say that all paths are covered? I mean,
no, I am not saying that when you make this conclusion, you use epsilon delta definition of limit.
Yes.
Okay, I'm not saying that if this is satisfied, then this will hold. I'm not saying that this. Are you getting my point?
So, sir, it was a coincidence.
It is just a coincidence. In this example, you get all these three equal.
Okay, sir.
From repeated limit, you cannot conclude the limit exists. Okay.
Yes, sir.
Any more question? Any more question?
Sir, you were going to talk about how to find the method. The last example you were talking about in the last class.
What I was talking about? Can you repeat it again?
Sir, the last example in the last class to find the limit.
You asked this question in the beginning of the lecture, right? Which example you are talking about?
Yes, sir. This one, sir.
This one. So, okay. So, what is your doubt here?
Good afternoon. Can you hear me?
So, I mean, how to approach a problem to find the limit? I mean, I was unable to grasp it yesterday, yes, sir. I find out it today, sir.
Okay. We'll wait for probably 2 more minutes
first,
before I start.
Let's say if this value is not given to you, okay? If this value is not given to you, then if this value is not given to you, then what you can do is you try to substitute this value. And then from there you can guess that there is a limit. If there is some finite number, then you can guess that this might be a limit. But this is only your guess. You have to verify this guess using the epsilon delta. Now, in some example, this may not work. When you substitute x is equal to, for example, in this case, when you substitute x is equal to 0 and y is equal to 0, you get 0 by 0 form. So in this case, this approach does not work for guessing the limit. So what we do is we take y is equal to x. We try this path to identify the limit. And if you take y is equal to x, you can see that the value of the function is approaching towards 0. So this path gives you a hint that the limit is 0. Okay. And then, so you can guess that probably limit of this function is 0. So then using epsilon delta definition, you can, you have to verify whether 0 is indeed the limit or not. Okay. In some case, this may also not work. In some case, you may have, this also may not work. Y is equal to x. So in that case, you go to y is equal to x square, right?
Can you see the slides?
You go to y is equal to x square.
Yes, sir. Yes, sir.
And then check
okay, good.
Whether you have some limit.
Today, I'm planning to start a new topic.
If you don't get a limit when y is equal to x,
catalysis.
If this goes to 0, then
I am supposed to take 6 lectures on this, including today's lecture. So let us see how it goes. So what are the topics that we will be covering?
The limit does not exist.
We will be covering homogeneous catalysis.
Does this clarify your doubt?
Yes, sir. So, sir, I was. Yes, sir. Yes, sir. Sir, I was also asking, sir. So when we need to show to find the limit, so sir, we have to follow one path, or we have to show 2 or 3 paths to verify the limit.
For verifying the limit, you have to use epsilon delta definition. If you do, if you verify the limit only along one path, 2 paths, or even countable number of paths, that will not work.
Okay, sir.
Because you can approach to the point x0, y0 from infinite number of paths, not even countable number of paths.
Yes, sir. Yes,
okay. For example, you may define a path y is equal to mx, and m can take value 1, 2, 3, and so on. So these are countable number of paths. By changing the value of m, you get countable number of straight lines, and along these countable number of straight lines, you go to the same point. But this does not mean that the limit is that particular point. Okay, so because it may happen that if you go along this path, you will not go to the same point as you were going along the path y is equal to mx. Okay?
Sir, you are not audible.
Yes.
Right. So be careful if you want to show that there is a limit. The only option available to you is to apply epsilon delta definition. That is the only option. इसके अलावा कोई मेथड कुछ भी किया इधर उधर सब गलत हो जाएगा. एप्सिलॉन डेल्टा डेफिनेशन यूज करो. एप्सिलॉन डेल्टा डेफिनेशन में हर एप्सिलॉन के लिए तुम्हें एक डेल्टा ढूंढना है ताकि जब तुम नेबरहुड से पॉइंट लो, डेल्टा नेबरहुड से कोई पॉइंट लो, तो फंक्शन का वैल्यू उस लिमिट के क्लोज हो.
Can you hear me now?
ठीक है.
Yes, sir. Yes, sir.
Okay, sorry about that.
केस में अगर कोई भी इधर उधर कैलकुलेशन
Let me share the slides again.
एप्सिलॉन डेल्टा एक ही अप्रोच है जिससे तुम लिमिट शो कर सकते हो. इसी तरीके से कंटिन्यूटी में भी यही अप्रोच है. एप्सिलॉन डेल्टा से ही कंटिन्यूटी शो कर सकते हो.
Okay, you can see the slides now. I hope.
सर मैं ये चैप्टर सर क्रीजिक ढूंढ रहा था सर, तो उसमें
what I was telling you, we'll learn about homogeneous catalysis, homogeneous catalysis, under heterogeneous catalysis.
So in my
we will
opinion,
talk about
just follow
surface
the
phenomenon,
slides,
porosity,
whatever is written on the slide, and then
Langmuir adsorption isotherm. We will talk about some mechanisms.
Sir, you mean
It is
assignment?
called Langmuir-Hinshelwood mechanism.
Yes, exactly. So
Radial
these
LA
two should
mechanism.
be your basic
And towards the end, we will
course
learn
material
about
when
how
you
to
prepare for this
use
course.
the
यही दो
activated
बेसिक चीजें तुम्हें
complex
करनी है.
theory
स्लाइड्स बहुत
when you
मेहनत
want to
किया है स्लाइड में
compare
मैंने. ठीक
the
है.
homogeneous
Yes,
and
sir.
heterogeneous reactions.
तो
These are the
बहुत सारी
different
चीजें
topics.
तुम्हें
Now, before I
चार
start
पांच बुक को
these
पढ़ने के
topics,
बाद फिर कुछ अपना एग्जांपल्स
anybody tell
बनाने
me
के
what
बाद
is
वो सारी
catalysis?
स्लाइड्स को समराइज करके एक सीक्वेंस तरीके से लिखा हुआ है यहाँ. ठीक है. तो अगर कोई भी बुक तुम फॉलो करोगे तो तुम्हें बहुत सारी चीजें इस स्लाइड्स में जो लिखी हुई वो मिल जाएंगी.
Yes, sir. The shifting of
लेकिन बहुत
reaction
सारी चीजें
pathway in order
तुम्हें
to
इस
get
स्लाइड में जो
a
लिखी हुई वो
faster
उस बुक में नहीं होगी.
reaction, in order to get the reaction faster.
ठीक है. जैसे पोलर कोऑर्डिनेट्स में
So
जब चेंज करते
basically,
हैं.
So I think
is reduce the obstacle in reaction.
it reduces the obstacle in the reaction.
Sir, catalyst reduces the activation energy in the reaction.
Increasing the rate of reaction.
Increases activation
Okay,
energy.
fine.
Area potential.
I am getting too many answers, but most of them are correct answers. Basically, a catalyst, it reduces activation energy by providing an alternative pathway. That is what people most of the time say about it. So without the catalyst, the reaction may happen, but it may be very, very slow. So in the presence of a catalyst, you have a faster reaction rate. Now the question is, what is the difference between homogeneous catalysis and heterogeneous catalysis? This is my next question. When you say homogeneous versus heterogeneous,
Sir, the reactants and
All the reactants and the products
in homogeneous
are not all same.
reactions and catalysts are in different phase.
all right, very good answer. So if the reactants, products, catalyst, everything is in one phase, we say it is a homogeneous catalysis. On the other hand, if it is not in the same phase, you have kind of a heterogeneous situation. Like for example, you have a gaseous reactant and the catalyst is a solid and the product is gaseous. So you have kind of a heterogeneous situation. So we say heterogeneous catalysis. So this is very, very clear. Now, what are the fundamental differences between these two? I have written some points which are very important. On the extreme left side, I have written feature, column title. When it comes to heterogeneous catalysis, what is it? When it is homogeneous catalysis, what it is? When you talk about the catalyst, from the stoichiometry.
Your voice is breaking.
Catalysis. Okay. Oh. Is it true for everybody?
Yes, sir.
Yes, sir. Yes.
Yes,
Yes, sir.
in between, sir. Yes, sir.
இல்ல இல்ல So, okay. Can you see the slide now?
Yes, sir.
Yes, sir. Okay, okay. If if there is any problem, let me know. So, on the other hand, I don't want to go very fast also. Let us see. Okay. When it comes to structure and stoichiometry of your catalyst, what is the difference between these two? Does anybody know? What do you mean by structure of the catalyst? What is mean by the stoichiometry of the catalyst?
The type of catalyst and the amount of catalyst with respect to the reaction.
Okay, when you say stoichiometry, all of you understand it's kind of the amount, how much mole, for example. When you say structure, around the, like, for example, if you have a metal center as a catalyst, around that metal, what is the coordination? So this is like, whether it is octagonally coordinated, tetrahedrally coordinated, this kind of thing, we will call it a structure. In the case of heterogeneous catalysis, this is not well defined. But in the homogeneous catalysis, this is well established. And it is highly reproducible. In the heterogeneous catalysis, you may have, for example, a surface. That surface, how often you can reproduce exactly the same. For example, you do the catalytic reaction today, and then after 1 week, you repeat the reaction. If it is a heterogeneous reaction, you may see some minor difference because the surface may be completely now little bit different in the terms of roughness, for example. The chemistry of the surface itself may have changed a little bit. So all these problems you may face the heterogeneous catalysis. Now, when it comes to active sites, now what is meant by active site? Remember, in a catalysis reaction, your reactant molecule, for example, may adsorb on a site. We call it as active site. The active site is, for example, in a heterogeneous situation, you will have on the surface. If you have a homogeneous condition, all the metal atoms can become the active site. The entire bulk. What is the opposite of the surface? Bulk. When you say bulk of the solution, that means everywhere it is happening. When you say only surface, that means the reaction is happening only on the surface. Obviously, in a homogeneous catalysis situation, the entire bulk may be involved in the catalysis. The active sites can be the whole metal atoms. Every metal atom of the catalyst can be involved in the catalysis reaction when it is homogeneous.
Sir, I had a small doubt.
Yes, yes.
When you said that in the case of a heterogeneous catalyst, after a week, we would observe that chemically the catalyst would be different after a week of
would
the
be different, may be different.
Yes, may be different. Yes, but
yes.
catalyst की definition ये थी ना कि it boosts it increases the rate of the reaction while decreasing the activation energy and doesn't change its chemical composition.
That is a very general statement. Doesn't change, little bit change. For example, I will take you an example. Suppose you are having a metal oxide as a catalyst. Okay, if I take an example, it will be very clear.
Okay.
So let us say magnesium oxide is the catalyst. So on the surface, what you are supposed to have? Magnesium 2 plus and O2 minus. Correct?
Yes, sir. Yes.
It will be on the surface.
Yes, sir.
Now, this metal oxide can have affinity, for example, towards carbon dioxide. So slowly what can happen to the surface? On the surface, you may have some magnesium carbonate formation. or you can have some adsorption of moisture, for example. Now the question is whether it will affect the catalytic activity. And the answer is it will affect the catalytic activity. It doesn't mean that your magnesium oxide has completely changed to something else. Only on the surface, we have very, very small amount, which is enough to change your rate, for example. That is what I am trying to say. So the surface.
So, sir, the chemical composition will change not because of the reaction, but because of other external factors, right?
Yes. Not because of the reaction itself. Okay, sometimes what may happen, another thing, since you asked me an interesting question, I can tell you. You are doing a surface reaction, you are expecting that all your reactant molecules convert into product and all the product molecules go out from the surface. The ideal reaction, that is what you will expect.
Yes.
But what will happen is some side products of the reaction may still get absorbed on the surface. So the cleanliness of the surface is very, very important in the heterogeneous reaction. So anyway, let us move on. I think I have answered your question.
Yes. Okay, I understood.
Let us go to the thermal stability. When it comes to thermal stability, for obvious reason, homogeneous catalysis, you can carry out only lower temperature, for example, 250 degrees Celsius or less. Whereas a heterogeneous situation, you can have reaction. You can have reaction at very, very high temperature also if you want. Now, can anybody tell me why in the homogeneous temperature usually we carry out at low temperature? What is the reason? Anybody guess?
Phase transition might happen.
So that is not adsorption can be done.
Okay, adsorption. Okay, I am looking for some answer. Why the temperature is usually less than some 250 degrees Celsius?
To keep the kinetic energy.
Sufficient collisions.
Okay, very good guess. Anything else?
Not much energy is needed for phase change.
Okay, I will come into picture here.
Exothermic process.
Okay.
Increasing temperature.
Let us try to solve this question. Okay, in a homogeneous catalysis, for example, I am having everything in one phase. I am having a solvent, for example. So my reactant is a liquid. My catalyst is a liquid. Or I have a compound which is soluble in that solvent. And I am doing the reaction. My products are also, for example, in the form of liquid form. So everything is one phase. That is why I say it is a homogeneous. Now, the temperature at which I am carrying out the catalytic reaction cannot exceed, for example, above the boiling point of my solvent. Most of the organic solvents in which you will be carrying out the homogeneous catalytic reaction may have a boiling point less than this, 250 degrees Celsius, most often. Can anybody tell me any liquid whose boiling point is greater than 250? Can you come across?
2SO4.
Which one? H2SO4. Anyway, first of all, H2SO4 itself, it is H2SO4 dissolved in water. Right? So do you think its boiling point will be greater than 250?
Sir, mercury?
No.
Mercury is not a solvent. Mercury is a liquid, I agree. But then it is not a solvent, correct? I cannot do a reaction in mercury. I'm talking about some routine solvents like, water obviously 100 degrees Celsius.
Carbon sulfide.
Carbon disulfide. Okay, you can look at the boiling point and tell me in the next class. And carbon disulfide, by the way, it's not a good solvent because nowadays people worry about whether your solvent is green. Does anybody know what is meant by a green solvent? It has some relevance to catalysis. That is why I'm asking this question. Green solvent. What is meant by that?
Eco-friendly. Doesn't have in harmful impact.
Eco-friendly. Okay. Eco-friendly. Okay. Liquid nitrogen, is boiling point is very, very low. It is first of all, it is not used as a solvent. It is used as a coolant. And its boiling point is very, very low, 77 Kelvin.
Sir, long alkane chains can act as a solvent, and as they are
long alkyl chain will not be a liquid, by the way. It will be kind of a solid. You can heat it at high temperature, make it melt. But then It may not solubilize the reactant because it is hydrophobic. Let us conclude or let us come to a conclusion. Most of the boiling
Sir, ethylene glycol.
Benzene, sir, benzene.
Benzene boiling point. Does anybody know what is the boiling point of benzene? It is less than water. Okay?
77.
78.
If I remember correct, my memory, if it goes, it is 80 degrees Celsius. Okay.
Sir, ethylene glycol.
Ethylene glycol is higher than, somebody Googled it and found it. Ethylene glycol is around 90 actually, boiling point. Okay. But again, it is a rare example. It is not very commonly used as a solvent. For example, I want to do organic chemistry reaction. Ethylene glycol may not be a good solvent. Okay. Because it is hydrophilic. Let us go to the, in general, the thermal stability of the homogeneous catalysis reaction is usually low. When it comes to heterogeneous, I can carry out the reaction at 600 degrees Celsius, 700 degrees Celsius, 1000 degrees Celsius. I don't have any problem. The only thing is I will try to lower the temperature so that I can reduce the cost of the process. Because when the temperature is high, obviously power input is very high. So I don't want. But homogeneous catalysis, in fact, people go for it. One of the advantages can carry out the reaction at high temperature. Whereas homogeneous cannot be carried out at high temperature as heterogeneous. So obviously the next point, reaction conditions, is related to temperature, low temperature. What about the catalyst life? Life of a catalyst. How long you can use the catalyst? Usually that is longer for heterogeneous. For homogeneous, it is shorter. There is something going on, correct? So when the life of a catalyst is short, what does it mean? The catalyst doesn't work anymore. Now the question is, why it doesn't work anymore? What has happened to the catalyst?
Active sites disappear.
Active sites get disappeared. Okay. Or active sites can get blocked by some other molecules. Okay. Some other molecules can go and attach to the active sites. This we call it as poisoning of a catalyst. Okay, all of you know poison. Poison kills. So in catalysis community, when you say poison, that means you are killing the catalyst. For example, there are many sulfur compounds which can kill a metal catalyst, like palladium. Palladium is a very common catalyst used in industry. But then when you have sulfur compound, it will kill its activity because rather than your reactant molecule, your sulfur compounds will go and attach to the active site. Okay. Now the next point, look at it. Separation. This is one of the very, very important points. When it comes to heterogeneous catalysis, it is very easy to separate the catalyst. But in the case of homogeneous catalysis, it is difficult. It is not impossible, but it is difficult. Now I will ask you one question here. We have three things. One is reagent, another one is product, another one is catalyst. These three are in the same phase. Now, how do we separate it?
Fractional distillation.
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 Fractional
If
distillation.
the boiling points are different, you can do distillation. Okay, I agree. But if the boiling points are close?
Fractional distillation.
That's why I said fractional distillation.
Okay, okay. Except distillation, can anybody propose any other method?
Freezing.
Freezing. Anything else? These are all older techniques. Nowadays, people go for something.
Distillation under reduced pressure.
Okay.
Potential extraction.
Okay. Okay. Chromatography. Okay. People use chromatography actually to separate the reagent from the catalyst. That is why it is written difficult. But it's not impossible. It is possible. The last point, the mechanistic understanding. So obviously, when you do a catalysis, remember catalysis is a very big field. There are textbooks written on catalysis and many industries are based on catalysis. So understanding the mechanism of what is going on is very, very important. Of course, if you are a chemist or if you are a chemical engineer, you will always worry about what is the mechanism of this reaction. What is the purpose? The purpose is Can I develop a better catalyst? If I understand the mechanism better, I will come up with some new ideas. Can I go for this metal? Can I go for another catalyst? So what are the different parameters that control reaction? Everything I try to understand. So in heterogeneous catalysis, the mechanism is not completely understood because it is heterogeneous surface for us. Surface characterization is not that easy compared to bulk characterization. I am making a general statement here. If you want to characterize a surface, it's not that easy. Again, I am saying it is not impossible. It is not that easy to characterize a surface. But if you have a homogeneous situation, there are so many experimental techniques at our disposal that you can use it to understand completely mechanism at the molecular level. When I say molecular level, what is going on? For example, if I have a cobalt complex, I am using as a catalyst. What happens to my cobalt oxidation state? What happens to the different ligands which are attached to the complex? Whether they go off, whether they can again come and rebind. Everything can be understood in the case of homogeneous catalysis because there are so many techniques, experimental techniques that can be useful. But when it comes to heterogeneous, it's not completely understood. So these are some important differences with respect to heterogeneous and homogeneous catalysis.
Okay. So this catalyst life, what was the explanation that you gave for it? Why is it shorter for homogeneous catalysis?
Why it is shorter for homogeneous? The catalytic activity gets easily killed because you can easily poison the catalyst in the case of homogeneous.
But what if we don't poison it?
Always in solvent, okay, you will always have some kind of impurity or some side product which gets formed that will be floating in your solvent only. The gaseous phase, most often they will escape.
Okay, sir, but a heterogeneous catalyst have only the surface, and this homogeneous thing has the entirety of the bulk. So
I understand. That is one way you are gaining. One way you are gaining that the entire metal atoms can get involved. On the other hand, the entire metal atoms can get also poisoned. Okay. So whether your reaction molecules get absorbed on the active site, that is what you want. But in a homogeneous situation, what may happen is there are other molecules which may be floating around in your solution because everything is in the same phase. In the gas phase, what happens? They can easily escape from the surface once it is produced.
Sir, okay. And this 250 Celsius is a general condition, right? It can exceed.
Amrit, can you repeat your question?
This 250 degrees Celsius is a general is a general case. It can exceed this temperature as well.
Yes. This is a kind of a general statement. It can, somebody was telling ethylene glycol can be a solvent, but ethylene glycol can be used at, for example, 250 and above. But there is one problem with that solvent also. That is, it is hydrophilic. You cannot carry out organic reactions. Okay, organic reactions, most of the compounds are hydrophobic. So suppose I want to convert benzene into toluene, my solvent cannot be ethylene glycol. Okay, let us move on. So
one thing.
Yes, please go ahead.
So the second point, catalyst separation and recovery. So why, what would you explain about homogeneous catalysis? Why
okay, in homogeneous catalysis, because all three are in the same phase, it is difficult to separate. For example, I want to recycle my catalyst after one catalytic cycle. So how I am going to separate it? It is not an easy process. I have to go through a column chromatography, for example. In the case of heterogeneous, because your catalyst is, for example, a solid, you can easily, from the reaction mixture, you can easily separate it. Simple by filtration. If your catalyst is magnetic, for example, in a heterogeneous catalysis, you can just apply external magnetic field and you can easily make the particles to attach to the magnet.
So these conditions,
I'm sorry, what?
So these conditions are not possible for homogeneous catalysis like solid.
It is not possible. It is not possible. It is not possible. That is why it is difficult to separate the catalyst.
So means homogeneous catalysis can never be in solid form.
No. If it is solid and liquid form, then you call it as heterogeneous only.
Okay, sir.
Okay.
Okay,
sir, I have a question.
Yes, Arian. Yes.
Sir, in a heterogeneous,
active sites only surface atoms.
Okay.
I mean, reactant reaction with surface atoms and
Okay.
homogeneous inside all metal.
Inside the we can say bulk, inside the bulk. Okay.
तो सर जो रिएक्शन फास्ट किस में ज्यादा होगी, होमोजेनियस में या हेटेरोजेनियस में?
Reaction fast homogeneous, I am going to go show you some data. Okay, so in which case you are going to have faster and which case it is going to be slower. Okay, you wait till my next few slides. I am going to give you some experiments.
Sir, in the case of active sites, when you are saying that the bulk atoms can also participate,
in the case of homogeneous,
yes, in the case of homogeneous, of मतलब जितनी मुझे knowledge है, तो जो catalysis होता है that is based on adsorption ना, और adsorption तो हमेशा surface atoms ही करते, तो bulk वाले कैसे
I think there is
करेंगे?
some misconception here. If you have a homogeneous catalysis, where does the adsorption take place? Does it take place on the surface? I am talking about homogeneous. Where is the concept of surface in a homogeneous?
हाँ, वो because मतलब phase separation के लिए कुछ होगा नहीं तो surface तो
There is
होगी
no
नहीं.
phase separation. The moment you have phase separation, you don't call it as a homogeneous.
Homogeneous. Okay. तो इसकी वजह से सारे metal atoms.
The moment you have a interface, whether it is a air liquid interface or a solid vapor interface or you have a solid liquid interface, then it is a heterogeneous situation. Is it clear? Let us go to the next one. Okay, this is one slide I just put it just to show you. See, every catalysis reaction is very useful. So we just looked at some points, homogeneous versus heterogeneous. But where in the industry homogeneous is used and where in the industry heterogeneous is used widely. Homogeneous catalysis is widely used for fine chemical synthesis. So does anybody know what is meant by fine chemical synthesis? What is meant by fine chemical?
Maybe, sir, crushed catalyst.
Okay. That way every chemical can be crushed, correct? So all chemicals are fine chemicals.
Like acid.
So that need to be totally pure, free of impurities.
Okay. What is the opposite of fine chemical? If I say ask that question like that, then you will be able to understand better. What is the opposite of fine chemical? Anusha, yes.
Sir, which are impure.
Impure, okay. You are very close. The opposite of fine chemical is bulk chemicals, okay? It is written here, bulk chemicals. For example, I try to produce tons of chemicals I want, like, for a specific purpose I want. I call it as bulk chemical synthesis. Most often, homogeneous catalysis is not used for bulk chemical synthesis. It's mainly used for fine chemicals. When I say fine chemicals, like, there is a chemical company called Aldrich. Okay, ALDRICH, Aldrich. This is a US-based chemical company. They sell chemicals all over the world. You will see that, they will have chemicals ranging from 500 milligram to 1 kilogram, for example, or 10 kilograms also. So when I say 10 kilograms, I say it is a bulk. But there are some chemicals I require in very small amounts only. For example, I may require only 500 milligram for finishing out the entire project. So I call them as actually fine chemicals. Obviously, it is going to be very highly pure and very expensive. So most of the fine chemical synthesis is done by homogeneous catalysis. And there is the next one, enantioselective catalysis, or which is also called asymmetric catalysis. This is also again homogeneous catalysis. Now, can anybody tell me what is meant by this enantioselective catalysis?
So maybe the use of enantiomeric pure catalyst.
The singly optically.
Very good. Very good.
It would only have levo form or dextro form. It won't be
yes, enantioselective catalysis is also called asymmetric catalysis. Many times you will find the two isomer of the same compound can have a totally different activity. For example, one can be antibacterial, another one is not antibacterial at all. Or one can be very toxic, another one can be very useful in the healthcare. So that is why in pharmaceutical industry they want to synthesize only one enantiomer. So we call it as enantioselective catalysis. Also it is called asymmetric catalysis. Most often it is homogeneous. And then when you want to make tailor-made plastics, homogeneous catalysis. When you say tailor-made plastics, what do you mean by this? Plastics with controllable property. For example, we call it as a syndiotactic polymer, for example. I don't know how many of you have heard this word. So if you have a main chain,
Plastic surgery.
it is basically plastics which have a definite conformation, for example. So these are all applications of homogeneous catalysis. Heterogeneous catalysis, obviously, they are also very much useful. Large volume operation. I want to produce tons and tons. I will prefer to go for heterogeneous. Bulk chemicals, petroleum refining. This is one of the very, very important process. Can anybody tell me what is meant by petroleum refining?
Cleaning of different layers of obtaining different layers through crude oil.
It is a refining of the petroleum, crude petroleum you are getting, right? So in this process, you will see there are so many heterogeneous catalytic process which is there in this petroleum refining. In the petrochemical industry, they have a huge section on heterogeneous catalysis. Okay? The number one reason, most of these catalysis reactions are carried out at very high temperature. Okay, anyway, let us move on. Somebody asked homogeneous versus heterogeneous, what will happen? This reaction, for example, nitrous oxide. Let us take the second example, decomposition of nitrous oxide. You can carry out this reaction without any catalyst. Homogeneous condition, you are just decomposing it. The moment you bring in a surface, you can see that the activation energy is lowered. Instead of 250, now you have 120. Obviously, remember the rate will increase exponentially. So you are going to have a faster rate about your homogeneous situation. The decomposition of hydrogen iodide, again you see that there is a reduction in the activation energy. These are some experimental numbers people have reported for some homogeneous reaction and in the presence of a catalyst surface. What is interesting is you are using gold, platinum. This is very expensive. But what about aluminum oxide? Is it expensive? Aluminum oxide, is it expensive?
No, not much.
No, aluminum oxide, there is a mineral which has aluminum oxide. Can anybody tell us? Like
Bauxite.
Bauxite is not Al2O3. Bauxite is the mineral for Al2O3. If you take bauxite and heat it, Al2O3. Corundum, very good. Corundum, yes. Al2O3 is actually corundum. Okay, that is a mineral name. Okay, now let us move on. Let me summarize what we looked at so far. We just introduced what is catalysis. We just introduced what is homogeneous and heterogeneous. Then we looked at what are the important differences between homogeneous and heterogeneous. We talked about catalyst recovery. We talked about active site. We talked about mechanistic understanding. Then few other points. Then,
excuse me, sir.
Yes.
Sorry to interrupt.
Yeah,
please tell me what was fine spelled like something. My speaker got disconnected.
Say it again. I did not understand.
In the previous slide, there was something fine chemical. My speaker got disconnected. Please tell it.
You did not understand what is fine chemical.
My speaker got disconnected. I did not listen at all.
Okay. So, homogeneous catalysis is used for making fine chemicals. Fine chemicals are the chemicals are of very high purity and made in small amounts. Okay. So usually fine chemicals, we don't get it in kilograms. Obviously, it's going to be very, very expensive. Okay. So,
Thank you.
opposite of fine chemical is bulk chemical. That is usually prepared by homogeneous catalysis.
Sir, what is initial selective catalysis?
I'm sorry, what?
सिर्फ fine के नीचे वाला initial selective catalysis.
Asymmetric. Okay, and asymmetric means you are trying to make out of two isomers of the organic compound, you are trying to make only one of them. Enantiomer selective. One of the enantiomer you are trying to synthesize. There are two enantiomers possible, for example. You are trying to make only one of them because the one which is useful you want to make, not the one which is not useful. Because enantiomers can have different properties.
Yes, sir.
Okay, let us go to the next one. You have to spend few minutes on this. Physics option versus physics option. How many of you know about this? Physics option versus physics option. Have you heard about this before?
Yes.
Yes, sir. Yes, sir. Yes, sir.
Yes, sir. In plus two.
Written some points here. Okay, I have written here. In physics option, we talk about weak forces are involved, like van der Waals forces. In chemistry option, the forces involved are stronger. This is one of the fundamental differences. Can you give me an example of a chemistry option process? I am going to give later on, but I am just asking.
Sort of chemistry option.
Chemistry option.
So rusting.
Rusting. Which is getting absorbed?
Haber's process.
Haber's process. Okay, actually when I ask this question, don't give you a catalytic reaction name. You can say that adsorption of so and so on some surface. Chemistry option. For example, I can give you an example. Adsorption of hydrogen molecule on palladium.
Sir, absorption of hydrogen and nitrogen on iron catalyst.
Okay. It's a very interesting point. Adsorption of hydrogen and nitrogen on iron.
Iron.
And the product will be ammonia. Is that correct?
Yes, sir.
Yes.
Okay. So, if there is a bonding between your adsorbate molecule and your adsorbent, the adsorbent in your case is a catalyst. Now, I will ask you another question here. What is the difference between an adsorbent and a catalyst? I will repeat the question. What is the difference between a catalyst and an adsorbent?
Certain adsorbent just basically is used to absorb a certain molecule or something, and it is possible that adsorption takes place, but there is no activation energy doesn't get reduced. But in a catalyst, it is for sure that the activation energy would get reduced, even if adsorption is not taking place in the case of homogeneous catalysts.
Okay. So any other answer? This is a good answer, but any other answer? What is the difference between an adsorbent and a catalyst?
The absorbent can react, but catalyst do not involve in reaction. It just gives a fast pace or slow pace.
Okay. Maybe I will try to interpret.
Catalyst can adsorb on adsorbent.
Okay. Catalyst can adsorb on adsorbent. This is a little bit confusing statement. Catalyst is a solid, for example. I am trying to adsorb a gas. So the fundamental difference between an adsorbent and a catalyst. A molecule comes, adsorbs on a surface, undergoes reaction in a catalysis reaction. But in adsorption, this may not happen. A molecule will come, adsorb on the surface, it may not undergo a reaction. So, adsorption is the first step of a catalytic process. But then adsorbent need not be always a catalyst. For example, activated carbon is routinely used as an adsorbent to purify water. But activated carbon is usually not a catalyst itself. In other words, it doesn't bring any chemical change for the reactant and then converting that into something else. So this is a fundamental difference. Now, chemistry option versus physics option, obviously the forces involved in physics option are weak In chemistry option, they are strong. And physics option happens at low temperature. And chemistry option happens at high temperature. This is the thermodynamics part. And physics option is most often reversible. And chemistry option is often irreversible. This is a very, very important. This option is reversible. What does it mean? Molecule come and absorbs, and then it can easily come out of the surface. Again, it can go and absorb. This is always under equilibrium. But in chemistry option, usually a molecule absorbs on the surface. It may not easily come off just like that. Unless the reaction happens, product forms. Then obviously you lost your original, whatever you started with. So chemistry option is often irreversible. Physics option has a stronger dependence on pressure of the adsorbate. What does it mean? I can have multiple layers of adsorption using physical forces. But in chemistry option, that is not true. Most of the time in chemistry option, it happens on the surface, obviously. Most often that will be monolayer coverage. What is meant by monolayer coverage? Anybody elaborate? Chemistry option is
a single only one time adsorption possible.
Of an atom thick.
Okay. Only one layer of adsorbate molecule is there. Now the question is, why only one layer? Why not multiple layers?
Because of strong forces.
Chemical bonding.
Bonds are being formed.
Chemical reactions are involved.
Because of the chemical
bonds are involved.
Okay, I will ask one by one. Shrey, can you tell why it cannot go beyond monolayer in chemistry option?
So because chemical reactions are involved in it, and in physiotroption, van der Waals forces are the deciding factors. They can exceed up to multi-layers, but chemical bonds can only be formed up to one layer, I guess, between.
Yeah, but the question is why it is only monolayer. Okay, the very good answer is that, remember, chemistry option, you have chemical bonding involved between an adsorbate and an active site. So the active site, you have it on the surface. As long as the active sites are occupied, we call it as a complete coverage. The moment the surface is covered with your adsorbate molecules, that we call it as monolayer coverage. Beyond that, your active sites are not available anyway. So the active sites only on the surface are involved, then that always most often lead to monolayer coverage. In a physical process, physics option process, since the bonding is very, very weak, you are not talking about any adsorption sites or active sites. Now the question is it possible physics option can happen on any surface? I said you don't need active sites. So that means physics option can happen on any surface.
What was your explanation for that chemistry option thing?
Chemistry option requires active sites. The active sites available on the surface, once they are occupied, you have no longer active sites available for further adsorption. So the complete coverage you will attain with the monolayer coverage of your adsorbate molecules. That's all.
Sir, it can't happen on every surface, but I think that it has a lower dependence on the adsorbate, as in chemistry option, chemical bonds are formed, and it is very reaction specific. So that's
monolayer, we are okay. Specificity we are not come into picture. The simple reason, obviously, chemistry option is going to be specific because that is a bonding. Bonding cannot happen everywhere. It will happen only with a particular site on the surface with another site on the adsorbate. That is correct. Now we were talking about monolayer coverage. Monolayer coverage, the moment you have fulfilled the entire adsorption sites, active sites available to on the surface, you have no more active sites for further adsorption. So you have already reached the complete coverage. So that corresponds to a monolayer actually. Okay, the delta H, this all of you may be familiar. The chemistry option is more exothermic compared to the physics option. These are some important points. Yes.
Sir, I have a statement that any surface have active sites is high. It means
Aryan, hold on. Just can you repeat your question?
sir, I have a statement कि कोई भी surface है वो बहुत
Okay,
ज़्यादा
the earlier statement I asked is in every surface, is it physics option possible?
Yes, sir.
Okay.
So it depends on the conditions like temperature, pressure.
Of
Sir,
course,
there
it
must
depends on
be van der
temperature.
Waals force of attraction.
Okay.
Because in physics option, van der Waals forces are universal. So
yes. So
it
the
can be
answer, your
attraction
answer is
between
correct.
them.
Provided the temperature is low enough, you can have physics option on almost every surface. So the only deciding point is, for example, the boiling point of the adsorbate. If you want to physics of nitrogen on your surface, you have to go to a temperature close to the boiling point of nitrogen. The boiling point of liquid nitrogen, some time back I was telling you, close to 77 Kelvin. Okay. So if you want to physics of carbon dioxide boiling point is much higher than that of liquid nitrogen. So you can, but then definitely it is below room temperature, the boiling point of liquid CO2. So as long as you have temperature low enough, close to the boiling point of the adsorbate you are interested in, physics option is possible. Always. And another point somebody was telling you that, the chemistry option is highly specific. It is correct. This option is not specific and chemistry option is specific. So that means some molecule will chemisorb on some particular surface, but it may not chemisorb on some other surface because of the chemistry is different. Okay, so it is enough if you understand this point. Chemistry option is highly specific. I am giving you some examples of chemistry option. Absorption of acetic acid on activated charcoal. Absorption of acetic acid on activated charcoal. This is an example of chemistry option. Absorption of nitrogen on SiO2. By the way, where SiO2 is used? Does anybody know? Nitrogen dioxide, where it is used?
So it is anhydride.
Bottles used to absorb moisture.
Acts to absorb moisture.
Okay, very good. SiO2 has many applications actually. It is used in pharmaceutical industry as a filler material. So what is meant by a filler material? You have active ingredient. You may have some filler material. And SiO2 usually has a very high surface area. You can use it as a catalyst support. That means you have a catalyst, for example, a metal. I don't want to use pure metal. I will put my metal on some material which has high surface area, SiO2, which I call it as a support. And SiO2 is also a very good desiccant. Activated silica, we call it. So it can absorb moisture. In fact, most of the electronic equipment when you buy, it will come with some small packets of desiccant. That is basically silica, we call it silica. So absorption of nitrogen or silica is a physics option. Absorption of acetic acid and activated charcoal is a chemistry option process. Now I will ask you one general question and then we will, I think almost we are done for today. I will continue the discussion. How do you differentiate experimentally a process is chemistry option or physics option? I will repeat the question. Experimentally, how one can find out?
Sir, with increase in temperature, chemistry option first increases and then start decreasing. While physics option rapidly decreases.
Okay. Let me put another question here. If I want to prove there is a bonding between the adsorbate and the surface, I will repeat. If I want to prove there is a bonding between the adsorbate and the surface, experimentally, how can I prove it? Bonding, I am talking about bonding.
We can try with another another, sir, absorbate. Some absorbate while other does not absorb.
The
This
net
prove that
enthalpy change and the net enthalpy change will be negative because bonds.
Okay, let us take this case. Okay, acetic acid. I am absorbing an activated charcoal. Obviously, I am telling you chemist option. That means there is a bonding between the acetic acid molecule on the surface of this activated charcoal. Now, how will I experimentally prove it? You are saying delta H you can measure. Okay, fine. That is colorimetry. Is there any other technique one can think of? The chemical bonding.
So we can actually test for the final product formed by activated charcoal and acetic acid, the characteristics of the final compound.
Okay.
We can measure the change in concentration.
The concentration of acetic acid will decrease.
Concentration of acetic acid will decrease. Obviously, because there is an absorption. Okay, from the solution, for example, this is the one way of finding out how much is really absorbed. But my question was something different. The bonding between
detected by the odor of.
Okay. I will give you some idea. Okay, just think about it. Acetic acid is CH3COOH, right? So CH3COOH means most often the carboxyl group is going to coordinate. So if the carboxyl group is going to coordinate, I can find out any experimental technique which can detect the carboxylate group. So obviously there are techniques available, for example, IR spectroscopy, infrared spectroscopy. The carboxyl group in acetic acid and the carboxyl group, if it is bonded to activated charcoal, there is going to be some minor difference. So this way you can experimentally prove that there is a bonding between the molecule and the surface. Okay, whether the adsorption has taken place or not, there are many ways of checking it. You can look at the concentration before and after. But the question is that doesn't tell you really whether there is a bonding between the molecule and the surface. I think almost we are done for today. It is 5 o'clock. So I can spend another 5 minutes if you have any special questions. Otherwise,
can you please once again tell how come we will differentiate a chemically bonded molecule to the surface?
Okay, let me take another example also. Suppose you say there is a carbon dioxide molecule which is adsorbing on, let us say, a metal oxide surface. So carbon dioxide has C double bond O, C double bond O, correct? Now, if I can get some information about, for example, the stretching frequency of C double bond O, before it adsorbs on the surface, after it adsorbs on the surface, if I have some information, what will happen if it is bonded to the surface? What will happen to the stretching frequency? Will there be any change?
Yes, sir.
They will increase or decrease?
It decrease.
Decrease. Why it will decrease?
What is stretching frequency?
Into the system.
What is stretching frequency? Very good. Okay, you have to read a little bit. If you don't understand, you ask me the same question in the next class. I think I have spent some time on this stretching frequency when we are talking about transition state theory also, correct?
Loose vibrational energy are talking about?
No, don't confuse loose vibration here. Stretching frequency is something different. Loose vibration is one of the stretching frequency mode.
Okay. That 3n minus 5 thing.
Okay. So,
excuse me, sir, I had a small doubt.
Yes, Ray.
Yeah, sir, when you were talking about the applications of catalyst, so what did you mean by tailor-made plastics?
Okay, tailor-made. Okay, so what does a tailor does? The tailor does according to the he prepares the pant or shirt according to the requirement of a person, correct?
Yes.
So when I say tailor-made plastic means according to my requirement, I can make a synthesize a plastic. That is what is meant by tailor-made plastic.
Yeah.
What is meant by, for example,
I can alter the composition of the plastic.
I can alter the property of my material. Tailor-made synthesis. That means what I want, I design my synthetic process in such a way that what I want. I want a material polymer, for example, with this much of glass transition temperature. This much of flexibility.
Yes, sir. It takes some time, but we are just giving idea. You can suppose even you search on the net, you can find out both scientific condensation, application, you will find lot of things. Okay, so I start my lecture. In the previous lecture, I was discussing, we are getting the BC, I discussed how we are cooling and finally we are getting one giant wave. And I also said, most of the time we are within only this region. We never reach 2 is equal to 0 because we have some limitations there. So we will be here. This is more than enough to do many experiment we are doing here. And basically we are somewhere in between these two conditions in real experiments. Okay, so I also showed these slides. We are planning to make a quantum devices all around the world and understand the quantum materials, and a lot of work is going on quantum technologies around the world. So many body system, I'm showing here a superconductor, how does it work? People are trying to understand some Cooper pairs. You will study when you will study the StatMech, advanced StatMech. So you will see all these things there. And there's something writing here, intricate quantum motion will electron give rise to imaging microscopic behavior. You will learn all this thing in theoretical condensed matter physics. And simulation on classical computer. Already many groups are working. So in classically, we have a some n bit describe the state of the system. So I'm showing you 2 up, 1 down, 2 up. This is also up, this is down, this is up. That is only one state given the classical word. Classical word, just I tell you in a simple way, other way. Let us say we have 2 states. If I'm writing here like this, 0 and 1. 0 and 1. Only in the quantum world, then we have a plus 1, this superposition state. That makes difference in quantum world. So classical world, either it will be 0 or it will be 1. In quantum world, not only 0 and 1 plus superposition of these 2 states. That make different. You can be anywhere. You can use many states. But thing is that once either you are in classical or you are in quantum. So भाई अंकित पटेल अपना माइक ऑफ कर दो. लग रहा मुझे ही करना पड़ेगा. So we can put in superposition the same thing I am showing here. I have already shared the slides with you already. Okay, we are putting all the are up, alpha 0, then 1 is down, we are writing alpha 1. This is the probability of finding the states. I will discuss maybe if I take quantum computing basic things, then here I am showing you now instead of this, now this is down, so alpha 2 and so on. There will be then 2 down, 3 down. So depend upon, so you can make out 1, 2, 3, 4, 5, 6, 7, 8. Basically to the power 8 states will come. If I am saying this is 1 state, 2nd state, 3rd state, and so on, to the power 8. So for simple example, if I am taking only 2, so if I am taking only 2 electrons, so either it will be like this, 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 or both down. So basically to the power 2 is coming 4, 1, 2, 3, 4. And so I'm talking in that way. Clear? So many states will be in the system. So let us, I'm calling this 1 state, this is 2nd state, this is 3rd state, 4th state. So we are using only 2 spins here, 1 and 2. That's why 2 to the power 2. Here I'm using 8 spins, 2 to the power 8. So basically you can calculate immediately. Clear to all of you? How many states will be there?
Yes, sir.
Yes, sir. Okay, good. So I'm showing here one of the most powerful computer. So I think up to here we discuss, and we want to make a more powerful computer, then we need only 56 spin. That I'm showing here, and I also shared this slide with also the ultimate supercomputer. So store one complex number in each atom in, let us say, in the universe I'm talking. So in the universe we have only that much atoms are there if we consider whole universe, and we say this information can be saved into 270 spins. Basically 10 I am writing like maybe 10 to power 3.3 something like this, and then if you are writing you can convert. So if you convert here it will come to the power 270. Basically I am saying this is equal, like on the previous slide, 10 to the power 80 is equivalent to 2 to the power 270. That thing I am saying here. Okay. So difficulty lies in the entanglement of the system. Still, many groups are working on this thing to get better entanglements in the states. Many work is going on around the world. So if we want to do something, we need a better thing. You need a quantum computer. But right now we don't have either a good quantum computer or not a good quantum algorithm. Many groups are working, and even Indian government also has invested a lot money on this to bring to come up. Still we are far behind from European country, American country, even behind China also. So immediate solution, quantum simulation, people are doing it already. So we have to, because once you have a cold atom, we can do quantum simulation, quantum computer, whatever we want to do. To use a well-controlled quantum system to simulate the difficulties access of quantum system of interest. Feynman says in this thing. So in one of my slide, I was showing you we are getting the giant wave of the BC. So in the coming slides, I will also discuss how we reached to make such a ultra cold atom. Okay, and one thing, my speed is going to be slow. I don't want to go very fast. So I'm just giving you the flavor. What is the how these things are working, why we are working, what is the region, and how we are reaching to the cold atom. So I will go with very slow speed, pace, and wherever you have questions, please ask. No need to feel shy. So here I am showing some device. We have to make the devices using the cold atoms. So which devices we are making, how making, I will discuss. So quantum simulation. So whenever we have a system, we have to write the Hamiltonian. Hamiltonian basically you just think if we have a kinetic energy part, potential energy part, add them. Some systems to tell about the system. What is the energy in the system? And then we solve it. We get some eigenvalue, eigenequation, all these things you will learn in the coming days. Once quantum mechanics will be introduced to you. So this type of system is very complex. We cannot understand immediately because all the atoms are very near, so we cannot predict anything, but we just can simply, the people are trying to understand, as I said, we are putting all this cold atom in a regular order, either in a single chain or in the 2-dimensional or 3-dimensional. Everything has been done in last 20 years. Many things has been done. So for example, I am showing here all that we have made some, you have seen the egg tray, you must have seen all of you. So just think instead of egg, we are keeping one atom here in a regular order. And what is the interaction between them? And then they are increasing and decreasing the separation, and they are doing the studies. How the medium works. Okay. So simple models we are making. You can say that this is one artificial material. So sometimes people have studied with the rubidium, sodium, cesium. Even they make the very heavy atom and very light atom, ytterbium, lithium. They made the molecule and put molecule in each of them how then it is behaving. So we are trying to understand, you can say, theory as well. The results are coming in the experiments. Can we match them, or what we should do it? So that the studies are going on last few years. So theoretically the concepts are very strong, but I said experiments are also going on. So here I am showing you must have read about the standing waves.
Yes, sir.
So what we are doing, we are putting one laser beam from here. We are putting one laser beam from here. So they make a standing wave, you already know. So wherever the you just think like this, in some places intensity will be very high and some places intensity will be very low. Well, zero you can say. If they are perfect, let us say I'm using some omega on both sides, and they have a, or I should say in terms of wavelength, I'm using, let us say, simple example, 500 nanometer.
We are reducing the temperature of the atom
nanometer.
to use
Then we are
them
superimposing it. Some places intensity will be very high. Some
for
will not.
quantum
Very
computing
intensity
and
is very
quantum
high.
simulation.
So we generally show in
I'm
a
not
form
going
of
in
potential
very
depth.
I'm not
Atom
telling me, I'm avoiding a question till now.
But before trapping it,
Except at
we
the
have to
Vogeli
cool the
wavelength.
atom, and its energy should be less than this.
So whatever I have taught,
So
and
the
next
atom
week,
can stay in the
when not next week, this is
laser
within
beam.
this week. I think Friday I have a
All
class
these
5 to
things,
6.
then how they are interacting.
I will take a
the
one
internal
quiz.
state.
There will be two
In
questions,
the present day, we can
and you have
put
to
the
send the
atom
answer in 10 15
100%
minutes.
fidelity.
And
Atom
that
is
will
put
be,
from here
I
to
will
here,
be
or we
grading
want to
from
take
there.
it here.
I will not
It will
take
be here
any
only. We have
exam
reached
later
up
on
to that
because you
control.
people will forget. So be there
So
in the class
for all
next
this
time
purpose,
also.
we need a ultra cold atoms. I'm writing here. So as I said already, we have a main aim here. We gain fundamental insight of the quantum mechanics and build the quantum devices. So fundamental insight, as I said, to understand the quantum materials, atomic clock. Right now, many groups working for atomic clock. So I will show you what is the region to get the best atomic clock. So you long back, 400, 500 year back when pendulum started, then they gave the definition of time, or time interval. Then they were using this phenomena to make the clocks. You must have seen the pendulum clock also. Now we have reached to the in atomic world where we can use the atoms. So to make the atomic clocks, they are perfect. Even for many years, there will be change in the second, fraction change in the second, it will not change. Otherwise, long back in my childhood, I was using the watches. So every 15 days you have to correct with the time, because in the winter it used to be slow, in the summer it used to become fast. Nowadays, present watch, all these things then doesn't happen. Even if you go to Europe or some American country, your watch will be keep on changing. If any change is there, it will be connected with the atomic clock of that country. You keep on changing the time. Suppose you go from the UK to the Germany, or you go to Italy, it's automatically change the time of local reference. They are doing in that way. So the highest accuracy we need. So for that, I'm writing here high tension frequency, optical tension, narrow tension. We need a very narrow tension when we are doing all these things. So we have reached millihertz, even less than the hertz we have already reached. And large signal if we want, then we use the many atoms. When we need a undisturbed by the other atom, then we use the gas of atom. So even we use the cold gas atoms, so they are not disturbing the other atoms, and they are also, I showed you, they are in a phase, so they give them very good signal. So observe for a long time, cool the atom to stand still. So all these things advantage of cold atoms are coming here. So people have already made frequency reference using the strontium. SR is strontium here. So strontium atoms in a lattice, they put this thing, and already clocks are made in America, Europe, Japan. They have already made it. Now, long back, cesium used to be reference of the atomic clock, but right now, maybe within a few years, let us 4 or 5 years, Instantium is going to be the reference of all atomic clocks. So don't worry, I'm just giving the idea. So even it has been shown when gravity change, time also change. So one of the experiment was done by NIST. This is the National Institute of Science Technology in USA. 2010, they did the experiment. What they did in experiment, there was this is the optical table I am showing it. They were doing the experiment here, and then they lifted this table by some height, and they found time changes, and they were this is one reference clock, okay, and they put their atomic clock on the optical table, and they were comparing the difference between the reference clock and this clock. So they found there is change of some 10 to the minus 16 order they are showing here. When they lifted this clock by 33 centimeter, and they found there is a little bit change in the time. So very small change, and such a small change, it doesn't matter to us in a normal way in the life, but when you using GPS at that time, these things matter very. This thing. Suppose you want to hit your position, or you want to check the position accurately within a few centimeter mistake, then at that time you need this better clocks. And they are also saying these constants of nature are constant. These constants also keep on changing. So right now they have already started this work. They have taken the strontium clock, ytterbium clock. This is another atom, and they are checking it. How much time will change between these two clocks. This work is also going on. So here I am showing some satellites in the space, and in your hand there is a mobile. The better they are synchronized with each other. Synchronized means they have the same time reference. Then the better information will get on your mobile. Even suppose you want to send one missile from here to here on the earth, you need a better synchronization in all the GPS satellites to get the better position here. At that time, this time matters much. Okay, so ultra cold as gases. So I have already said what means which gases we are using. For purpose of making some atomic clocks, some other simulator things, and how we are going to cool them. These atoms that I am going to discuss in next few slides. So basically, what happened? This was given by the Bose-Einstein condensation, this paper, maybe in around 1926 at that time. If we want DEC, in that case, this rho is defined as the phase space density. That should be greater than 2.6. And what is this rho? Basically, this is n lambda cube dV, de Broglie wavelength. So we have to increase this number such that this should be greater than 2.6 if we want. And making this 2.6 is not easy. So basically you think in that way, this n is 1 over d cube. This is the distance between the two atoms. Or you can say like this. So basically we have to increase the number of atoms per unit volume to increase the n. And then de Broglie wavelength, I said de Broglie wavelength increase when temperature decrease. So we have to cool them. So we cool them to increase this, and then increase the number of atoms per unit volume in such a way we should get 2.6. Clear to all of you?
Yes, sir.
So we have to bring the suppose one atom is here, one atom is here, one atom is here. Basically we have to bring near to increase the density, as well as we have to increase the de Broglie wavelength by reducing temperature. We should follow this condition. N lambda cube dV should be greater than 2.6. So we need a high density and low temperature. So here I'm showing lithium, they are solid. So we are making the gas, lithium, sodium, all are solid in real. Rubidium, cesium, but we work with the gas only. So free atoms are not a ground state of the system, they are solid. And then we have to, I'm just writing here 3-body recombination, don't worry too much. Basically, theory was given that when 3 atoms collide, so 2 of the atom will be cool down and 1 will be go out. With the 2 atoms, they could not explain theoretical model, but it was explained using the 3 atoms. We call it 3-body recombination. When they hit each other, 2 of them cool down, 1 goes out from the cooling. So we have to get this density, limit density such that decays time scale longer than experiment of interest. So this 10 to the 14 centimeter cube, because we are using gaseous, rubidium, cesium, whatever. And just to give the example, density of the air in the whatever we have in nitrogen, little oxygen, hydrogen, all that is 10 to the 19 centimeter per cube, 10 to the 19 atoms per centimeter cube. Here we are not going up to that high. We are lesser here. In real experiment we reach only up to here, 10 to the 14 per centimeter cube. So we need a atom density this much, and we have to reduce the temperature of that range. If you multiply and find out the de Broglie wavelength, certain atom, you will reach around 2.6 to get the BEC, Bose-Einstein condensation. So in the laboratory, here I'm showing one, we don't have a refrigerator. We have to use laser beams. So laser beam, they make the atom anything hot, they can cut the sheet. You must have that. You must have that somewhere. But here we are also using again in the quantum optics thing, we use the laser beams, atoms, and all these things to cool the atoms. So here we are taking some atomic beam from the oven, some atoms are coming, then we are using some cooling layer, cool down the atom, but that is not enough. I will discuss all these things. So before going to this thing, I am going to discuss about the quantum particles. Okay, there are 2 types of quantum particles found in the nature. One is boson, one is fermions. So you have already heard Bose-Einstein condensation. So that is a bosonic particle, and they are also fermionic. So boson like to do the same thing. So what is the meaning of this? Okay, all of them have a same nature. Okay, fermions are independent-minded. So I got some picture, but they are not like a boson. So here I am showing atoms depending on their composition can be either boson or fermions. The simple theory is this: each atom has a electron, proton, and neutron. Each one is a half integer. If any atom has an even number of this, then that will be a boson. Or if any atom is odd, summation of the electron, proton, neutron, if their summation is odd, then that will be a fermion. Let us take a simple example. This is lithium 6, lithium 7. Lithium 6 has 3 electron, 3 proton, and 3 neutron. So total is 9. So 9 into half, this is a half integer is coming there. It's not an integer. So this is a fermions. But in the lithium 7, we have 3 electron, 3 proton, and 4 neutron. So this becomes 10. Multiply by half, this is integer. That's why this is boson. Have you got the point? Any atom that is composite of electron, proton, neutron, if they have an even number, then this will be a boson. If this is not an even number, then it will be a fermion.
Yes, sir.
Okay, so just remember, you will read all this thing in the coming years. So why I'm telling all this thing? So what happened? Bosons integer spins, and there's some states you will also learn this thing. Basically, I just want to say in a harmonic potential, all these boson they go into the ground state. They sit in the system's ground state, all the atoms. Okay, but in the case of fermions, they are independent, and there is even Pauli exclusive principle. Pauli exclusive principle says in a one state, well, more than well, they are one spin up and one down. So two, if they are fermions, two fermions cannot sit together unless they are different. So here we have taken the spin up and down. So they can sit, but not more than two they can sit here. That is due to the Pauli exclusive principle that you will learn in coming year. So basically what was happened difference is here in the case of boson, all the atoms are ground states. So that is the lowest energy state. Here you keep on filling up. So they reach, maybe I have put this should be here. Line my mistake, this should be here. If this atom is filled up to here, so this is called Fermi energy. So all the fermions will not go to the ground states due to the Pauli exclusive principle.
Excuse me, sir.
Yes.
So does that mean that bosons do not follow Pauli exclusion principle?
Yeah. Yes.
And so many bosons can be described by a single quantum state.
Yes. The giant, I said they make a giant wave. That's why I'm showing here one giant wave state.
Yes, sir.
Is showing here. Okay, but in the fermion case, they will not go in all the ground state. They go one by, though they are spin one half downside and this half upside downside. So they have a different. All the quantum numbers are different. We say generally in a normal way, कि only different fermions can sit together. Since they have a same nature, they cannot sit together.
Okay, sir.
In a simple way. So here we don't use the word BEC, we use the Fermi C. There we are using the, with boson, we are using the BEC, Bose-Einstein condensation. When in the case of fermion, we say Fermi C of atoms. So here they go to the, they start from the ground state after cooling, but this will be not the lowest energy. They will be a little more higher energy than BEC. So we call it Fermi energy. So people did it also. So that was experimentally it was shown in 1995. It took another 4 years to reach up to here. So you can make out it's not so easy. People took 4 years to reach up to here. So they were working at that time with lithium atom only. Lithium 7. Because around 26 model was given, 1995 experiment performed. In between, lot of laser discovered, electronics improved, vacuum instrument improved. So that's why it took some time to understand all these things. So an analogy for Bose-Einstein condensation. So you know ordinary light or laser light. So whatever difference between ordinary light and laser light, I am going to show here. When ordinary light, it divergent. Divergent means when you have a bulb, you switch on, the light is going all direction. That I want to say. But in the case of laser, it goes only one direction. Incoherent. If whatever light coming from here, whatever light coming from here, they will be not in phase. So that's why we are saying this is incoherent. They have a many small waves. Small wave, whatever pulses are coming, they come in small pulse, not a long pulse like this, continuous. And many modes. So what happen is going in this direction, so they have different frequencies. So that's why we use the word modes. But in the laser case, it has a directionality, but little bit diffraction losses are there. it's less in this light, but still diffraction is there. You must have read diffraction in class 12 when light fall on the aperture. So some pattern forms here, diffraction pattern. You must have read this thing. So that depend upon the aperture size. Even you put the laser light in an aperture, it will diffract. And then further, it is a coherent. Coherence, simple thing that if you have a double slit, you must have read the Young double slit. Aperture 1, aperture 2, if light falls here, or you say laser beam falls here, you see the fringes here. Dark, bright, you see here. So that basically depend upon the coherence. So that's why I've written the coherent. And if you take the, instead of laser beam, if you put the bulb light, you will not see the fringes there. Because that is incoherent light, so you will not get the bright and dark fringes. One big wave, so when laser light is coming, it's a very long wave comes. That is happening due to the coherence, or vice versa you can say. And it is a single frequency. Monochromatic, actually we use the monochromatic word. Mono means single, but laser light even comes from the laser. It is not a single frequency. Nowadays, best thing is we use the word quasi monochromatic. Even light comes from the laser. It has also some line width. Let us say 1 megahertz. Suppose if you have a helium neon layer, even you see the diode layer, you must have seen some pointer layer. You have center frequency. In that case, line width is around 10 to the power 9 hertz. You can say 1 gigahertz. But it's not a single frequency. So here I am just showing the bulb we have replaced by the ordinary gas, and laser has been replaced by the Bose-Einstein condensation. They have the same property like this here. So atom flit around the randomly. So we say them they are divergent, incoherent like this. If they are marching in lockstep, so they have these properties. That's why I showed first example of ordinary light and laser light. Clear?
Yes, sir.
Okay, very good. So these I am showing the images. When they were taking the ordinary gas, images come like this, same thing, BEC. Here we are showing most of the atoms are cooled down. Same, so this thing. Now we will discuss how this thing we do in the experiment. So here I am showing one atom. It is a nucleus. The laser light, when it's like this, 1 minute. So this atom, so I am showing one laser, some photon is coming here. So you know this photon has some momentum. It will transfer the atom will absorb that photon, and it will get the momentum. So I'm showing you that when it will excite to the upper state if it absorb. The condition is this will happen only when this difference between the two levels should equal to the laser light. Laser wavelength I'm saying, or this lambda, this should match. Then it will absorption will take place. I think that much you already know, all of you. So this I'm showing photon can absorb, it get the momentum, then it will emit the light, it will go in this direction, then atom will again get the momentum this direction. It will be very small, we cannot measure it, but we know it can be calculated up to which order, even very, very small, we can calculate it. We have reached up to that limit now. So right now I'm showing, let us say one atom is moving in this direction. And if atom is moving in this direction, it's not, I'm showing here one light come, but it did not absorb. Reason, when atom moves due to the Doppler effect, absorption peak will change. Doppler effect you must have read. That was on the sound and all this thing. But this happen also in the atomic world also. If atom is moving due to Doppler effect, its absorption peak shift. So we have to take care of those things also. So if we have a right frequency, so we are showing it absorb it. So how do we slow the atomic beam? So I'm showing here some atomic beams are coming from the source, and we have a slowing laser from the right direction. So this is open, it's an atomic beam. And if laser beam is coming here, so what happened? Atoms, so these atoms, they will absorb the laser and then slow down. But you should remember, when atoms are coming from here, they have a distribution over all velocity. A certain velocity group is there, from 0 to some number will be there. Not a single atom, because we are heating the atom, so different velocity group will come out. So when laser beam comes here, so when it was found experimentally, only certain velocity class he cool down, not all the atoms. Only a certain velocity, or either you keep on changing the laser frequency, then you can cool down all the atoms. So right now I'm just showing you when due to the Doppler effect, I said one of the resonance will match, atom will come resonance. The atom that is in resonance with the laser, they will cool down. So to improve this thing, so what people do, they use the Jeevandam slower. They put some coils, magnetic coils. So what happens when we apply the magnetic field to the atoms, their energy level shifts. Right now, suppose these two energy levels are there. When we apply magnetic field, so the energy levels may be shift like this. Separation increase between them, decrease between them, but whatever you want to do, you can do it. Not decrease, I basically increase. So here whatever showing.
So with the help of the magnetic coils, we uniform the motion of the.
No, we are not uniform. No. We motion will be the same. We what we are doing, we are increasing separation between the, even they are going out of resonance from the laser line, but their separation will keep on increasing such they will be always in resonance with the laser light.
Okay, so more and more more and more particles will cool down with this.
Yes, yes, that is the main thing.
Okay. Okay, sir. Okay.
Sir, how is this gap actually increasing, like due to the magnetic field?
Which gap?
The energy gap, like so that they are in resonance with the laser.
No. Initially, suppose this much gap, then you can see here magnetic field is B1. By 1 minute. Here magnetic field is B1, here B2. So B1 is more than B2 because we are using, it means the coils are more here. So more coil, more magnetic field in the center along this. It has, let us say 100 Gauss. So I will say this is 0 Gauss here, magnetic field.
Understood, sir.
Understood.
Okay. Yes, sir.
So this way we are doing this thing. There should be always resonance. So even atoms are coming here. We are showing more and more atoms, velocity reducing. So we showing here number of atoms are increased here. Lower velocity coming more here, because I said in one place in the beginning, we have to increase the density of the atoms. We need more atoms. So, but this is not enough to make the density. Even this trick is not enough. So people, what they did, they use the more and laser beams from all direction, 6 direction, that I will discuss in the coming slide. So like this.
So can't we use multiple a laser with multiple wavelengths? I mean, two, 3 different laser beams with multiple
I'm showing
wavelengths,
here.
so that
You are right. We are using, see here, 6 beams. You can see here 1, 2,
so
3.
but these are
4,
from
5.
different. So but these are from different direction. I'm saying that all of the beams come from one direction only.
See, you are right. But let us see. For example, If,
Okay,
for
sir.
example, I am using the rubidium, okay, and each layer cost me something like 30 lakhs rupees. Multiple layers, suppose you want to use a 5 layer, so you 150 lakhs rupees. And I have a limitation of money. Then you have to find out the trick. With minimum expenditure, you can cool and more atoms.
Okay, sir. Understandable,
Okay.
sir.
For
Yes,
example,
sir.
if
Yes.
anybody is working in a sodium, that layer system costs around almost 100 lakh rupees. 1 crore, you can say. Then he need more layer system. 5 crore rupees only go in cooling. When we do the
Okay, so
research,
basically we have to take in consideration the economic factor as well.
yes, that is factor because we are working on the tax paying money, man.
Yes, yes, sir. Makes sense.
Institute giving money,
Yes,
that
sir.
is coming, government is giving, is coming from someone's pocket. Agree? So when we do the research, you have to take many,
Yes, sir.
many factors.
Yes, sir.
Okay.
Understood. Thank you, sir.
Okay. So what happened? Here I'm showing the magneto-optical trap. So initially, here it was. Initially they were using the 6 beam they use. And these 6 beams are coming only from one layer. One layer we take, then we make divide in 2 parts. Then another layer again divide in 2 parts. We have all suppose this is the 30 milliwatt. So we are getting each 10 milliwatt. We have all these optics parts are there. We can divide. So what happened is whatever figure I'm showing you, you just think in this way: x, y, and z, and other side is minus x. This side is minus y, and so on. Minus z. We are putting beam like this. In this case, atom, whatever cool down, we become like a molasses. Molasses is sugar when make in the factory, that form something like that. So you can see, we have seen, if you come in future, I will show in my laboratory. It's appear atoms group somewhere here, sometimes it goes to this side, sometimes it goes to this side. It keep on moving left side, right side, but it's not in the same place. It comes there, but not in the same place. It's moving. You can feel something moving in the within a vacuum system. So to make it more at the position dependent force, some position, some particular position, all these atoms should come. So what we did, well, it was suggested in 1980s around at the time. They put the 2 coils, anti-Helmholtz. One current is going this direction, other current is going this direction. So basically you can say in the center, this is a zero magnetic field. So all the atoms are forced to come at the zero magnetic field. So whatever we are putting this coil, 2 coils, current coil, and this 6 laser beam, so they magnetic, these laser beams, they meet at the zero of the magnetic coils. So I use the word anti-Helmholtz. Anti-Helmholtz means currents are flowing in the opposite direction of the 2 coils. One you can say this side, other this side. This is understood. That's why magnetic will be zero in the center. And this type of, when we use the 2 coils, they give quadrupole magnetic field. Sorry, my this jumped. So quadrupole magnetic field in the sense, magnetic field will be this and this is showing my coil, and some magnetic field will be something like this. It look like coming from here, going up, north is there and going toward the south, something like this. And the center they are zero. So what happened? So along this x-axis, the magnetic field will be a little linear. I'm showing here the linear magnetic field. It behaves like in linear. And on this x-axis, we are saying By, Bz components are zero, especially when you are on the center. Of course, both along whole axis, I should say, along whole axis. These By, Bz components are zero. And under this point, Bx will be also zero. So what happened? I'm just to consider the simple one-dimensional this thing. Even I will not explain this thing because you people have not read the atomic physics fully. Once you learn the atomic physics, then meet me. I will explain all of you, because we have to use some energy level, magnetic sub-levels. So, for example, if ground state has a 0 and this state has a 1, we call it something like this. You just try to understand. Okay, we have a quantum number L. If this quantum number L is equal to here 0, this has a 1, and submagnetic levels come from 1, we can write +1, 0, -1. So this thing I am showing here. So basically this model was used to explain how the atoms are, why the atoms are pushing inside. So this is right now my limitation to explain all of you. So this model was used to explain why atoms are coming inside and why laser is in resonance and pushing the atom back to the center. Center in the sense where magnetic field is 0. Okay? Don't worry. I said don't worry about the mathematics of the model, but just you understand we use a 6 laser beam. There were overlapping in a region where magnetic field was 0. And all the atoms are pushed to come there. So these I'm showing laser beams. So basically it's in resonance, this position, and this position. So they're pushing the atom inside. So magneto-optic trap. So I'm just showing here ytterbium atom, cold atom come look like this. And these people also got the Nobel Prize. I have already told Stephen Chu, Kohn Tanuji. Kohn Tanuji has written a very nice quantum mechanics book. You people, those who are interested in quantum mechanics, they can go through these books. And this William D. Flip. And again, problem is there. The temperature, the limit. So what happened? Even you cool down the atoms, still they keep on absorbing the photon. Once they keep on absorbing the photon, so they will be not cool down. That's why I'm saying that T equal to 0 is very difficult. So that thing I'm discussing here. Okay, density, whatever limits. So how the limits comes? The photon heat through a atom. So suppose we are putting the light continuously. So even those atoms are cooled down, still they get absorb the atom, because what happened? Those atoms, whatever laser light is coming, even they are cooled down, with the center frequency they are away. Center frequency will be not absorbed, but laser has some line width. The lowest part they absorb. So they keep on pushing the atom from the center. So then people come with the idea, once we have cooled the atom, transfer the atom in other laser beam. So we call it let us trap and cool the atom without near resonant. Let us add now, once we cool the atom, transfer them to a other laser beam that is far away the resonance. Far away resonance come in the sense, let us say, suppose you people have read, say sodium light. How many wavelengths are in sodium lights? Anybody?
2.
The class?
2.
5, 8, 90 and 96 angstrom. ये पढ़ा ना?
Yes, sir.
Okay. So if you are laser, suppose this is the energy levels of the sodium, and this is the, let us say right now I'm taking 5890. If you put the 5890, the atom will go from this state to this state. But if you, instead of 5890, you take some other wavelength, let us say it has a, let us say, if I say 9000 angstrom, so it will go only up from here to here only. The atom will not absorb. So this is without near resonance, meaning is this. You are far away the resonance, atom will not absorb. But this layer we use to hold the atom. So we call it optical dipole trap. We can hold the atom in other laser beam. So you already know, okay, suppose this is the atom, In the center, there will be some nucleus, some electron out. Basically, go to quantum world. So this is a nucleus, and there is a cloud of electron. So that's why I'm showing here the cloud of the electron has been shifted toward this side of electric field, and center has been shifted this side. So here, suppose when we are using some laser beam is coming that has oscillating beam. So when it moves, it keep on oscillating like this. So we use this beam to hold the atoms. So I'm not going in that thing in very details. Just understand. We use some lens. Laser beam comes, and we focus. We focus the beam like this.
Sir, a laser beam consists of what?
Photons.
Photons.
Electromagnetic wave, or you think into EM wave.
Okay.
It's a EM wave. And we cannot make any laser beam cannot be focused in the sense this direction less than the wavelength. Still we can focus some tight focusing like this. So in my laboratory we get around 30 micrometer. Even we have we have reached 10 micrometer also. But generally 30 micrometer. We can focus up to that much laser beam. So we can, in some laser beam is coming here. So for example, I am using 1064 nanometer beam. So we can hold the atom. This is the cloud of the atom. Whatever we got in the magneto-optic trap, we transfer the atom here. These are trapped atomic clouds. Once you hold the atom, so we have to cool them like you have seen the tea cool down when you cup in the tea or coffee. So same way we do cooling. How we are doing cooling? See here. High energy atoms we are taking out. We have techniques. High energy atoms they are going out.
Sir?
One net.
The optical trap.
Finally they have come all bottom. Tell me.
Sir, like we did this cloud and laser, the dipole experiment because the particles can absorb photons and thus get energized, right?
Yeah.
But what if we do the optical trapping thing like with the lasers in a dark room itself?
In a dark room?
Yes. So
yeah, we do only in a dark room. We don't use it's everything in a dark room. See, even your dark light doesn't matter. See, even 1 minute, I go back. Suppose you have I'm talking about sodium atom, okay? You're in a room and sodium has two wavelengths. Let us say I'm talking 589 nanometer. Instead of angstrom, I'm writing nanometer. And in your room, there is one bulb or tube light. If it's not giving this wavelength, nothing will happen to this system. It will not absorb. Atom,
so,
that's why we are making.
So why do we need a dipole trap? Like if it's not like the primary purpose
of dipole trap, see, we have to cool the atom. See, once we have got the MOT, but we are now unable to get that required number of density.
Okay, understood.
We are not getting. So there are many other ways. This is the optical dipole trap. I said there are people use two more ways to cool the atom. So now we transfer this atom to the laser beam from here in a laser beam.
Understood.
And then this laser beam is work like a harmonic oscillator. What we do, we slowly reduce the intensity of this laser beam. So first trap was this. Then we make a trap little small. One trap coming like a harmonic oscillator. Then we made little trap like this. Then finally trap like this. So that all suppose we are putting the atom, they are coming out. High energy atom we are sending out. Finally we reach a limit. This become very small. Only cold atoms are left. That I am showing here. I can show again this movie. This you can, maybe I don't know the website is still exists or not. I took from the Jila Physics 2000 web. So here they are showing all these atoms. High energy atoms are going out. That we are going out by reducing the depth of the trap. Depth of the trap, harmonic oscillator is like this. Then we make little smaller, so that high energy atoms should go out. So they are going out. They are going out. Finally, all the atoms come to the ground state of the system, and this is the BEC. So what thing is that how to measure it? That I'm showing here, thermal clouds are there, and they are within the dipole trap. So atoms are falling due to the gravity. This is a CCD camera, charge coupled device, and this is a lens. We are putting the laser beam from outside. Images comes here, so you can make out this is the what is the distribution of the atom, and we do in different timing. So and suppose BEC is there. When BEC fall, so we switch off the laser beam, dipole trap laser beam. It's coming down, coming down, coming down, coming down, coming down, and then pass the laser beam. The only difference is this: whatever previous image I showed, that was a little more circular. BEC case, it's elliptical, and I said in delta x, delta p of the order of h. So if I go in the beginning, you can see in this direction, it is very small, delta x very small. So when we drop, that side expand more. Momentum is more in this direction. So that was the signature of BEC. So this formula happen only in the quantum world. If your delta x is very small, the delta p will be higher. So that's why atoms are moving in this direction faster when they are dropping. So the BEC image came, and people got this first time when they got the Nobel Prize. This was the Cornell and Wyman group. So this was the simple cloud, when some cold atom and some cloud, and finally this is BEC. This shape is elliptical. Some other group, Catalan group, MIT, they got in November. It took, they were using some different trick. They also got it, and they also got this is Catalan, and these two, and maybe I have my one slide could not come. I showed the what is the application of the slide by my mistake. So maybe I will take one more lecture of you. I will ask Lalita ji. The next lecture I would like to take on the quantum computing, basic of quantum computing, how we do it, and what is going on around the world. So whatever you have a question, I will. My one slide is missing here. What is the application of this thing? So if you have any question, now ask me.
Why do we use these as block elements like sodium, rubidium, and not the D block elements?
See, people have already all depend upon the which lasers you have right now. That is very important. Suppose alkali atom, let us say lithium, potassium, sodium, rubidium, cesium, they have a single electron outside, and all this they have a lasers are there already, and easy to understand these atoms. If you see the history, people started from with the sodium long back, and they were also working on hydrogen, little tough, and hydrogen BC are also made. People have made already hydrogen BC, and all depend upon, I said, ki lasers. So you cannot use helium neon laser to work with the rubidium. You need for rubidium, you need a 780 nanometer laser. For cesium, you need a 852 nanometer laser. For sodium, 5890. For potassium, 786, and for this I think 760. 670. Sorry. Something like this, all wavelength. So it's not easy. So nowadays, in last, let us say 25 years, solid state lasers have come. They have a chip, small chip, and they are playing and they are working on they are using all these things. And
Sir, lasers will lose out their energy, right?
Laser, we are using lasers to cool down the atoms. Obviously.
So lasers are opposing atoms, right?
Yeah, but yes, suppose as a center MOT, so in the center, if any atom want to go this side, the laser will push him inside.
So sir, photons have no mass and lasers are pushing atoms.
Yeah.
How is it
happening? This is happening because when anything, this atoms, photon has come, atom has absorbed, it has gone to the upper state. Okay, so laser photon has some photon is there. Photon has a momentum hk. Hk means we have h bar means h over 2 pi. K is here 2 pi by lambda. You must have read that momentum is
h by lambda.
h by bolo. Photon has a momentum.
So sir, how is atom pushed?
Okay. So what happened? I'm explaining it. Atom has a levels. So when laser has come here, so it will go to the upper state. Let us say from this state to this state. It has absorbed. Now momentum is transferred to the atom. But when atom will emit the light, it may emit this direction, it may emit this direction, it will going to emit in all directions. So overall, momentum transfer will be 0 while emitting the light. Because it continuously photons are coming. Photon is not one, it's an infinite number. So from the laser, infinite numbers of photons are coming. Every time it absorbs. But when it emits, photon can go this direction after emission. So overall net transfer, that will be 0. So whatever momentum transfer is happening only in one direction. So atom is coming from this direction and laser is coming from this direction. So this will cool down.
Sir, if laser are not of accurate wavelength, then atoms will escape.
Yeah, then they will not talk each other. That's all. That's why I said we generally suppose this is the atom, so we keep the layer somewhere here. So let us say this separation I am showing here, we keep in my laboratory we keep around 12 megahertz.
And also, sir, it also depends on atom, no? Where it will de-excite.
So this 10 to 15 megahertz. Not all the atoms if you go, they are between 10 to 15 megahertz. You have to keep the laser little just, and we have a technology to reduce the. How do we reduce the frequency of the laser? That we have a technology now.
So which lasers are present in our laboratory?
I am working with rubidium, so I have this laser.
Okay.
Sir,
Hmm.
sir, does the structure of atom changes in DEC?
No. That's why we are making atomic clocks, na? They don't change. Either you are here or you are on the Mars or you are in a Jupiter or you are another way of the side of the world. The structure will going to be the same. Atomic structure never change.
But sir, since the density is high, so the intermolecular attraction will increase and...
No, these are neutral atoms. These are neutral atoms. You think in other way. There is no interaction in that way. I just neutral atom. I did not talk about if there is interaction between them.
But sir, you said that in BEC see they got interlock, sir. What that interlock actually
Interlock,
means?
they are in the same phase. Suppose they are giant wave, they behave in the same way. Whatever one atom will do, same thing other atom will do. Just like you think in the laser, na, all the photons are locked. They are going in one direction. So they also, nowadays people are doing atom optics. So in the laser optics, you are using laser, and they have already made the atoms laser. Atoms are going in a synchronized way. Instead of laser is going from here to here, they are making atom laser. You can search on the net. You will laugh. That atom laser hardly can go maybe less than 10 mm.
Okay, sir.
But they are learning because atoms they don't change their behavior actually. So if you search on the net, you will find atom optics, and people are working on it also. And these atoms, whatever I am discussing, they are also using these atoms for quantum computing. Already many groups have shown the quantum gates. Now they are making the processor. Many groups are working on it. You must have read Google, IBM. They have already made it. They are using superconducting qubit. Some groups are using NMR, this non-magnetic resonance type of thing. Some people are using ions. They are charged atoms basically. Some groups are using only atom, neutral atom. Many ways are going on to make the quantum computer. But in the future, most probably, some hybrid type of quantum computer will come.
And
सर
sir,
सो इसमें डॉपलर इफेक्ट को मिनिमाइज करने के लिए क्या करते हैं?
हाँ वही बोला Doppler effect. See, Doppler effect, we call it Doppler. We use the Doppler effect here, not Doppler effect is there. I should say, see, when atom is moving in this direction and laser is coming from this direction, so I tell you what happened. That frequency, let us say, atom has laser has a frequency omega L. Okay, so I'm writing frequency, angular frequency I'm writing. And atom is moving with the velocity v. So this omega L, this means when atom and laser are coming too near, the frequency will increase. So we give this formula actually, k dot v. That should be equal to the atomic frequency. So laser frequency we keep less. So we know what is the order of, once we are pushing the atom with the 6th laser beam, we know what is the order of this kV. So because this is a one-dimensional case, so we just remove the dot, just write down this kV. So generally that's why I said we keep this laser. This separation I said talking, this is 12 megahertz. We keep the laser 12 megahertz away from the resonance, and we have a all scheme for it. We use some, we call it AOM, acoustic modulator. This is used to shift the wavelength. So we are standing in an era where you can control everything. You can even lock the laser frequency will not change. You can do that thing, and even laser intensity will not, frequency will not change, intensity will also not change. Many things are there. So maybe I will take one more lecture on quantum computing. I will ask Lalita ji, give me one more so that I will discuss a little bit of basic of the quantum computing and how does it work.
Sir? Sir, is it easier to make cesium BAC rather than lithium BAC since the size of cesium is more than the lithium?
I tell you, when this BEC game was going on, so Jila group, They were using in rubidium. Okay. And MIT group. They were using, I think, sodium. And the group who made first time MOT, cold atom, French group, LKV, where Kohn Tanuji was there. They made a blunder mistake. They took the cesium atom. And these group, they got it first, BEC, but this group could not get it. And it took another 4 years to understand why cesium BEC is not coming. So they have one phenomena, we call it scattering length. Later on, cesium BEC also came. People made it. But it took some time because whenever they were trying, their BEC used to collapse. Whatever peak you're seeing, all the cold atom collapse means all the cold atom used to run away from the center. So first they published one paper, it cannot come. But after some time, there is one phenomena, we call it scattering length. So one group, they applied high magnetic field and they changed the scattering length and they got the BEC. It's depend upon where you are standing, what is easy to get. It's just luck. Some people are working rubidium, sodium. Nowadays, most of group working on strontium atom, some ytterbium atom, because they have a 2 electron outside. More, it need more theoretical physics, complex system. So it's not it's your choice. Whatever atom you can take, whatever you want. People are working with the holmium atom also. And iridium, indium. But for this, you need a laser wavelength near about 350 nanometer. It's not easy, UV light. So people are first making 700 nanometer, then they are doing frequency doubling. So more and more optics are involved. You can check on the net. If you search BC, it's their application. I missed my this Google Drive could not. I think I made a mistake. I will share. In the last sheet I showed you what is the application of this thing. I could not show.
Okay, sir. Thank you, sir.
So should I stop here?
So,
Thank you,
the quiz you were talking about last week, will you
I'm
conduct
planning
now?
maybe tomorrow I will send.
Oh, okay. So after your next lecture.
Should I take it tomorrow? I should take or after next? Okay, I will suppose Lalita ji allow me to take next lecture on Monday. Then after my lecture I will take. If she didn't allow, then I will send the quiz tomorrow.
Okay, sir.
It's just a simple question you have to answer in your. Don't.
So tomorrow any time we'll try to
After
keep our.
let us say 12 o'clock, submit by 5 o'clock.
So if possible, we can even do it now. We don't have any issues. Like we thought it's
But
now.
मैं जरा tired हो गया इतनी सारी slide बनाते बनाते.
And sir, we have workshops also.
To be very honest,
at
we have a
6:30.
lot of load right now with the assignments and stuff. So maybe after our next lecture would be like,
Okay.
if possible.
I will ask Lalita ji if she allow me. I will inform you also. Okay, I am taking next lecture.
Yes, sir. After next lecture, it will be okay for all of us.
Yes, sir. Next lecture.
Yes, sir. And tomorrow may not be convenient for some people since I'm actually traveling tomorrow. So.
Okay.
Tomorrow is
Okay,
not
on Monday. Let us discuss with Lalita ji. She coordinating this PH-101. So Monday maybe I will take class. I will request the other faculty also. Okay.
Okay, thank you, sir.
And somebody had written, sir, please send the slide in the Teams group. I sent in the Teams group only. I send in my this group. Slides are there. Or I will send it by today. This also whatever I have. In fact, I found my 2-3 slides have not come here. I don't know where I made a mistake. I will share those things also. Okay. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Bye.
Sir, next.
Next, I will take maybe Monday. I will ask Lalita ji.
सर मंडे
Yes,
मत करिए,
please.
मंडे को क्लासेस रहती हैं.
ये मेरे मंडे की तो क्लास है ना. मंडे की ट्यूसडे का होती है. ट्यूसडे. When I have a class 4 to 5.
Sir, Monday.
Monday है ना? Monday के 4 to 5. So I will give the quiz and you will submit by 9 o'clock. You will not take more than 15 minutes to answer my quizzes.
Oh, okay, sir.
Understood.
15. Okay.
Sir, in the quiz, like just to confirm, we'll just have to know the concept behind like whatever you have taught in the class, right? Nothing special.
I will not go beyond that. See, actually what happened, if I take later on, you will forget everything.
Yes,
you understand
sir.
my problem also. That's why, see, I tried my best not to show any equation, not to go in that. I'm just giving the flavor of the field. To students who have not seen yet, if you were here, then I would have told more and more things, so that because I'm seeing your faces, then I can understand whether you're understanding or not. But in a online class, we have a limitation also. You understand? You can understand my limitation. I understand your limitations.
Yes, sir.
Suppose in the class, by seeing your face, I could make out whether you people are understanding or not. Then I would have gone more down. So take it easy way. Don't worry. Though go in there's no need to worry. And in fact, 2 years back, we had one student here. Her name is Ria. She got job in this Microsoft package of 2 crore rupees from our department. So I'm sure few of you will also go in a big company, a big package. So keep on doing hard work. See you in the next lecture.
Thank you, sir.
So the girl was in physics?
Yeah, EP.
Engineering. Okay, sir.
Okay, bye-bye.
Thank you, sir.
Bye, sir. Thank you, sir.
Plastics with controllable